Excellencies, distinguished panelists, ladies and gentlemen, good morning and welcome to an online regional workshop on 5G Testbed Initiative at IIT Delhi, jointly organized by IIT Delhi in partnership with Telecommunications Standard Development Society India, TSDSI. I am Mudassir Ahmed Bakshi, PhD student of Bharati School of Telecom Technology and Management, IIT Delhi, and a host of this workshop on behalf of IIT Delhi. I would like to take this opportunity to express my sincere thanks to the organizers and in particular our outstanding panelists for taking their precious time to join us. Even though they are very busy with their responsibilities and we truly appreciate their dedication. So first I will give a brief introduction. So what is 5G Testbed Initiative? Actually, it is a multi-institute collaborative research project on 5G indigenous testbed and is being executed with participation from 8 institutes: IIT Bombay, IIT Delhi, IIT Hyderabad, IIT Madras, IIT Kanpur, IIC Bangalore, CEVIT and Samir. Each institute is contributing to the testbed in a complementary manner based on their expertise and interest. The expertise spans from antenna design on one end to the service layer architecting and designing on the other. So at IIT Delhi, we are developing innovative solutions in the areas of energy harvesting in IoT systems, security, light fidelity, cost-effective air pollution monitoring system, multi-access edge computing with haptics application, selective algorithms in massive input, multiple input and multiple output systems, massive MIMO. So I will describe the agenda for today's webinar. The agenda is like we will have an opening session that will include an address note and a keynote which will be given by Professor Huzur Saran sir and Professor Brijesh Lal sir respectively. After that, an expert talk first on multi-access edge computing will be given by Professor Arzad Alam Khirani. Then we will have a break of 15 minutes. After the break, an expert talk second on massive MIMO algorithms will be given by Professor Saif K. Mohammed. So we will, in this webinar, we will be, describing mainly multi-access edge computing and 5G new radio channel estimation, equalization, and blind decoding of control signals. So therefore, this workshop will provide us not only essential knowledge, but also a great opportunity to share experiences both on technical and regulatory basis. So just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box in your GoToWebinar control panel. We will bring them up during the presentation and maybe we will also have time for questions at the end. Now, without further delay, we will start this session and turn the time over to our presenters. I first welcome Professor Huzur Saran sir to provide an address note to this session. Let me introduce and give a brief sketch of Professor Huzur Saran sir. Professor Huzur Saran is a professor and previous head of the Department of Computer Science at IIT Delhi. Prior to joining IIT Delhi in 1990, he did his PhD in computer science from the University of California, Berkeley in 1989 and a BTech in electrical engineering from the Department of Electrical Engineering at IIT Delhi in 1983. His research is focused on computer networks and algorithms. Prior to this, he was the head of the Amarnath and Shashi Khosla School of Information and Technology, IIT Delhi. Professor Saran has been actively working in 4G and 5G wireless technologies. During 2000 to 2002, he was a visiting professor at the Information Systems Lab, Stanford, where he worked on the media access control layer of an exploratory 4G wireless systems. He has been investigating wireless access and mesh technologies to enable information and communication technologies for remote regions. Professor Huzur Saran sir is the principal investigator of the project building an end-to-end 5G testbed in IIT Delhi. So I welcome now Professor Huzur Saran sir. Mr. Asif, you can switch to Professor Huzur Saran sir now.
Sure, Mudassir.
Hello. Okay. You can switch to Professor Huzur Saran sir.
Is he joined? I can't see him in the panel.
He is not here.
Not yet. Can you remind him?
Okay. So is Professor Brijesh Lal sir present in the panel?
Yes, already he is.
Okay. Okay. So we will let Professor Brijesh Lal sir to give a keynote speech, and let me first introduce and give a brief bio sketch of Professor Brijesh Lal sir also. Professor Brijesh Lal completed PhD in 1997 from IIT Delhi in the area of multi-rate signal processing. He joined Hughes Software Systems in September 1997 and worked there for nearly 8 years in the signal processing group. He returned to his alma mater and joined IIT Delhi as a faculty member in 2005. Since 2005, he has been in the electrical engineering department and has contributed to research and teaching in the general area of signal processing. He has successfully completed numerous sponsored projects and consultancies and is working on several others. He was trained in Bharati School of Telecom Technology and Management, IIT Delhi, and is the coordinator of two centers of excellence, namely Airtel IIT Delhi Center of Excellence in Telecommunications and Ericsson IIT Delhi 5G Center of Excellence. He is the co-PI, principal investigator of the project building an end-to-end 5G testbed in IIT Delhi. So over to Professor Brijesh Lal sir. Please welcome Professor Brijesh Lal sir. Yes, Asif, Mr. Asif, you can now switch to Professor Brijesh Lal sir. He can address.
Morning, everyone. Am I audible?
Yes, sir.
Yes, sir. You can switch your camera. That will be great, sir.
All right, let me see if I can switch the camera on.
Okay. Yeah.
Am I visible?
Yes,
Yes,
sir. Are there any presentation, Mudassir?
No, I'm not using any slides.
No.
I'm just going to talk about.
No. Yes, Professor Brijesh Lal sir will give a keynote address.
Okay, great.
Yeah,
If you can flash the agenda or something else, that will be better for.
Yeah, please flash the agenda. That's a good idea. And I will start. So, welcome to this webinar. Now, the idea here was that a lot of initiatives in the area of 5G have taken place over the last few years. One of the major Indian initiatives has been this 5G testbed by 8 institutes around the country, funded by the Department of Telecommunications, supported by bodies such as TSDSI. So this has been, without doubt, the most significant effort in the area of 5G testbed development in the country. So in continuation with this effort, what we are now trying to do is reach out to the people and let them know the development that we have been able to achieve. And given that we have certain features and functionalities already available and certain others which will be ready by October, how can the rest of the ecosystem leverage this capability? So in line with these webinars today, we're going to talk about two areas. One is MEC, and the other one is about the baseband processing engine that has been developed at IIT Delhi along with the researchers at IIT Madras and CVIT. Of course, the details of what we've done there will be provided by the respective leads in that area. Professor Arzad and Professor Saif have contributed significantly to those areas. Today, I am going to talk about 5G in general, what it means to India, and what are India efforts vis-a-vis the 5G initiative. And towards the end, we'll talk a bit about the test bed. So what is 5G about? So ever since the advent of wireless communications way back in early 80s, and then it's very, very widespread deployment in the 90s, especially the late 90s. And then after that, of course, it became commonplace around the globe. The focus had been to provide first voice connectivity and then later data connectivity. But at all these times, the fundamental idea was how to connect the user better, how to give him the capability to speak to another person, and how to interact with the data that is present in the net, and enable some data services, the kind that you hitherto or till that point in time used to be able to consume only over Ethernet. So this is how the standard was improving over the years, and we finally reached 5G. And in 5G, there's been a sea change in the way people have looked at the standardization effort. In 2G, it was about getting most number of people connected wirelessly and provide to them wireless voice capability. So that was the only service that people had in mind when the initial deployments happened way back in the 1990s, I guess. So after that, what happened was, towards the later stages of that particular standard, people realized that there's also this need for data on the move. And some early efforts to be able to transmit the data were made. But because the underlying technology for communicating data was circuit switch based, the data also that was handled was the circuit switch. So you had high speed circuit switch data as the first offering in the area of data. And very soon people realized that packet switching is the way to go forward. And thus GPRS and Edge happened. And that allowed us to transmit data using packet switching, and which also meant that because now you were using a protocol that was more amenable to the kind of traffic that you expect in data, there was wider usage. And suddenly people realized that this has potential, and people just don't want to speak to each other. They also need access to reliable, high quality data connectivity. And therefore, when 3G happened, there was of course talk of providing a video chat facility, but also a clear move towards providing more data services. And this is the time when phones started getting more capable. You had feature phones in 2G, and the moment you moved towards 3G and towards the latter half of 2G, the advent of smartphone happened. So there was this transition to move from the feature phones to smartphones, phones, so that the device that you used to carry around with you changed. So the way you interacted with it, instead of using keys, now you had a touch interface. Cameras got better, and the ability to run more complicated apps which required more than just voice and SMS capability started proliferating. And the same thing happened for iOS and Android almost simultaneously. Things like Symbian, which used to be extremely popular in feature phone days, started losing out to these two technologies. Then people realized that data is extremely important, and voice is a relatively thin pipe. So people started focusing on data. 4G was about data, and you improved the access, you improved to some extent the connectivity towards the core and the core functionalities. But the thrust here was to provide higher bit rates to the end user, and also support packet switching more uniformly and more all over the ecosystem. And some of the people leverage that by making voice over LTE more popular. So you might have heard about Volte as something that some service providers around the globe offered. The reason for that was that once you have packet switch, you have a reasonably thick pipe, and voice is simply a very thin pipe in that reasonably fat and competent pipe that you have available with you. So what do you do with it? So people started using it to send packet switched data. So VoIP evolved to something like voice over LTE, and people were talking to each other, not using the traditional circuit switch to 2G kind of data only. They were also speaking using 4G, where there was packet switching the voice data as well. So this is how things evolved from 2G to 4G. Uh, as people started thinking about 5G, there was a sea change in which, in the way people approached making this specifications. For the first time, rather than look for improvements, when the designers went to the drawing board, they thought about what is it that such a system should achieve, what is it that it should give to the user. So for the first time in the development of these systems, the designers were looking at performance before technical specifications. So that is why in the early days when we used to look at 5G, you used to hear terms such as 100 times faster, maybe 10 to 100 times quicker, more robust, and such things. So people started talking about performance metrics, and of course building technologies to make those happen. Some of those techs already existed, others had to be built on top of existing techniques. So that is what happened in 5G. It started with the idea to look at the ecosystem and see what are the kind of applications people want to run over the next few years, and what are the kind of network capabilities will make that happen. And that is why you came up with that nice circle where people used to show that in along the 8 different axes, how was 5G much better than LTE in all of those parameters. The other change that happened as we moved towards 5G was the move from feature phone to smartphone was a very organic and a very incremental improvement in the handset or the device that you use. However, when you move to the space of 5G, there is also inorganic growth in terms of applications are being added, not just by the kind that improve the bandwidth capability of the access, but also things like concurrency, ensuring latency, and that is why you see that triangle flashed so often whenever there are talks on 5G, where people talk of enhanced mobile broadband as one of the vertices of the triangle, but there are two others. There's talk of what is known as massive machine type communications, which is about concurrent connections, which means that a lot more people, well, not people within quotes, lot more devices can connect to the network simultaneously. This is the need that is driven by the burgeoning IoT ecosystem and industry. A lot more people realized that you do not need human intervention in a lot of activities that are happening around us, be it a house, be it a campus, be it a factory, be it a city. You can sense a lot of things in the environment, take inferences, or you could collate that data and present it to a human to take decisions. So the need for concurrency led to what is known as massive machine type communication, and this is being leveraged and will find its way into smart factories, smart campuses, smart cities, and this is something that will happen. Then the last or the third vertex is what is known as ultra reliable low latency communication. So whereas this was MMTC was about a lot of low end devices connected to each other, with ultra reliable low latency you're looking at very high end devices, the devices that cannot make a mistake and devices that cannot afford latency or delay in their operation, and hence the poster boy application, remote surgery. You could be in anywhere in the globe, and the surgery is conducted by the top surgeon in the globe, and he's able to do that remotely because he has access to tools, and you have access to a robo who responds instantaneously to the commands that are given by the surgeon at the other end, and the surgeon is immediately able to feel what is happening to you so that he can make corrections on the go without having any adverse impact on the health of the patient. So ultra reliable, low latency communication all of a sudden made it seem like, magic could be done. You don't really need to go to another place to have access to the best facilities in the world. Uh, and this is something that what is easiest to relate to, but this is not where your LLC ends. Applications such as hazardous, work that you do in mines, where split-second decisions have to be made. Incorrect decisions can result in catastrophe. Uh, have also been enabled by this ultra reliable low latency communication capability. So what has happened is that now the wireless technology is not about connecting to people in a robust, high bandwidth, low latency manner. It is about also enabling infrastructure around us so that our life in general becomes more comfortable. A big change that has started to happen and will only become quicker as time progresses is the automation of transport. More and more vehicles are coming equipped with the capability to sense and at times take decisions and fire actuators, which means steer, brake, increase the acceleration, choose a different route, and so on and so forth. All of this is made possible by the fact that 5G supports a lot of inherent capabilities in the technology. It allows multiple connections, it allows high bandwidth, it allows low latency, and because of this, what happens is vehicles can speak to each other, vehicles can talk to the infrastructure, and infrastructure, of course, is connected to the cloud and to each other. And what all of this means is that now you have guided pathways on which your vehicles move, and your vehicles are hearing from the environment, they're talking to the environment. And what this means is that the possibility of accidents or wrong routes reduces because the cars are talking to each other. So the car in front would let the car behind it know that it's slowing down, or whatever else. Infrastructure would let it know that you have to expect such a thing because there's a crash that's happened a little distance ahead, and things like those. So what 5G has done for us is that all of a sudden 5G is not just about talking to each other or surfing the net or streaming video. It has evolved to encompass all the different areas of our life: health, well-being, calendars, meeting people. Over the last year or so, we've interacted a lot more with each other over the internet, and this is an example of that. And this has been by no small means enabled by the widespread deployment of 4G. 5G will only make this better and easier. And while talking about video conferencing, in the space of video conferencing, what 5G can do is move from a high quality video conferencing experience to what we call immersive experience and shared experience. So what happens is you exploit AR and VR because 5G has not been growing in isolation. There's another technology that has made a lot of headway in the last few years. AI ML is gaining ground as quickly as the wireless is, if not quicker. And that's possibly because it has applications in a lot more areas, and 5G is still being deployed. So anyway, so given that AI ML and 5G are both evolving at a very quick pace, and they are not evolving in silos, they are willing to talk to each other as technologies, and researchers are now in the area of 5G willing to explore possibilities of how AI ML can play a role. So what this will do for you is that AR VR, augmented reality and virtual reality, will actually become possible in the near future. What this means is that the experience becomes even more immersive. Some of you might have already experienced with some simple attempts made by current application providers where you seat people in an auditorium, you build a stage, a post where you speak from and stuff like that. So that is the very early steps people are taking in the space of augmented reality. Augmented reality is about presenting the reality, augmenting it with information that you want to be present. So you have a person who's speaking, whatever he speaks is presented, but his background or the place where you see him seated or standing is augmented to make it more realistic. This kind of experience is important because humans are very perceptual in their interaction with the environment. You have to feel from more than just your hearing and seeing senses. There are 5 senses, and you react to all of these. You've grown up to expect certain things to happen, and therefore the talk of what is called immersive experience requires you to recreate the real world in this virtual world. On the other hand, there's something known as virtual reality, and in virtual reality what happens is you move to a very different space. Everything moves to the virtual space, and now you are represented by your avatar, and the environment that you build is the kind that you want. And clearly there is a lot more possibility in VR than there is in AR, because it does not have the handicap of including some real entities in the scene. So VR is another space which is changing the way people game. It is changing the way people share experiences, and AR is the way people are changing the way they experience communicating with each other. So you see immersive videos where you try to augment reality by making it appear that all are sitting in a room. But moving forward, what is expected is things such as touch, haptics, as it's called, will also become part of the communication modality, in which case there will be another sense that will start playing a role, and eventually you'll also have the sense of smell, temperature, and all the other things that e-skin can do will become part of your experience. So what that means is that you can now have an experience which is very close to being in the same room face to face without actually traveling to a particular site where all of you get together. So shared experiences, immersive conferences, immersive shared experiences, virtual reality, augmented reality, all of them are being enabled in a lot of applications that a lot of smart developers are making around the globe. But the reason they're able to do that is one, 5G, and two, AI ML. And what is now happening is, as we move beyond 5G, there is a convergence, a very, very strong convergence of AI ML and wireless communication. You will see in MEC that for the first time there's a very real converge between communication and computation. You have now a smart edge device which not only caches, which not only communicates, but it also computes. So it is way more capable than the other base stations that you're normally aware of and the kind that you've been using. And the end effect is that your experience is optimized. It is as good as it possibly can be given the constraints of the network. Now, going beyond, what is going to happen is this is going to become more and more commonplace in almost all devices, endpoints, equipment that are present in the 5G ecosystem. So you'll have a lot more of this happening in the core. You'll have a lot more of this happening in the management servers, where a lot of decisioning will now be left to the machine to do, because the machine would have intelligence, within quotes. What is intelligence here is for another day, but it would have within quotes intelligence to give resources to different parts of the network efficiently, so that the users are not ever denied the quality that they've opted for, and the service provider ends up getting the maximum profit without compromising the experience of the user. So this is going to also become commonplace in your user equipment, a lot of new flagship phones and even the medium quality smartphones have engine for neural processing. So neural engine is something that's becoming a reality in almost all current generation smartphones, and the reason for that is you want a lot more decisioning on your phone as well, because some of the apps will need it, and at times it will also improve the way you communicate. So AI ML convergence is something that is driving the next generation of communication, and I will say a few words about 6G before I close, with a few things about 5G. And one of the things that will happen in 6G is what I term as consolidation. So 5G has, at times it appears to people bitten off more than it can chew. Let us see how much of the promise it will be able to deliver. But whatever promises it is unable to deliver are not losses, because in the next generation, what people are now trying to do is consolidate the gains that have happened because of 5G being such a capable and such an ambitious standardization exercise. So in 5G, in 6G, one of the things that will happen is a more all-pervasive advent of AI ML in the entire network. And the second thing that will happen is not leaving anybody out, ensuring that just as there was a thrust on the kind of applications you want to support, a lot of applications that we think of can now be supported with the technologies that we're trying to build. But there are still remote regions that we cannot connect effectively. So there are parts of the globe that lose connectivity, which are important for holidays, which are important for societal needs, such as remote rural setups that you have all over the globe. While you're at sea or while you're at war. So there are multiple applications that exist which require robust, high quality connectivity at all times. And therefore, the other thing that will happen in 6G is ensuring more ubiquitous performance capabilities around the entire geography of the globe. So having said that, let's come back to 5G for a while and end this talk with what is happening in the space of 5G. So 5G currently has three kinds of things happening simultaneously. On the one hand, the final few releases are being built by the specification bodies or the standardization bodies. A lot of manufacturers along with service providers are deploying some capabilities of 5G, and the research community, given that a lot more is now possible, is in a frenzy to come up with innovative apps, probably push the boundaries of the technology that are available, and provide experience which is way better than what we are used to. So you'll have smarter devices with more capable applications and more immersive experiences. You will have environment that senses your presence, understands your state, and gives you recommendations accordingly. A scenario where you, on your way back from home, the house knows what time you'll reach, so the air conditioner or the heater switched on, it is at the right temperature when you reach there, because the house knows what the traffic conditions are, it knows how your car's moving through the traffic. You reach home, the door opens for you alone, nobody else. You enter, the right set of lights are switched on, you are guided to the right food. The refrigerator will tell you that given your mood, given the kind of work that you've done, the kind of calories you've burned, this is what you should eat for dinner. Your TV will switch on to the right programming, or the music will come on, the lighting will be right for the occasion. You will be told about any pills that you might have to take, or any task that you might have to complete before you probably move to your sitting room. And all of these things, given today's tech, given 5G, given AI, can be made a reality and have been made a reality in a lot of environments, and it is just going to become more commonplace in the times to come. So in the end, there are a couple of words of caution. The one thing that we have to be very, very careful about is that as we become more and more dependent on technology, we challenge ourselves lesser and lesser, which is not necessarily a good thing. Fewer and fewer people are now working to provide for more and more people. So the comfort that researchers and engineers work for is something that becomes available to the entire community, the entire set of people. Well, at least the ones who are able to afford, and the ones the government is able to provide to the not so rich, become used to the lazier way of life, if you will. However, if you have somebody else making all the decisions for you, you challenge your brain less, you challenge your body less, and therefore it becomes imperative that you do not lose track of the fact that humans have been evolving for only about in the form that we see them, maybe 20-30,000 years, and the kind of changes that we are trying to make to our environment are the kind that would need evolution of a few thousand years, if not more. So we cannot just shut off our bodies and try to live the world that the machines are going to present to us. So we should be very, very aware of the fact that technology is moving at a pace which is way faster than the pace at which your bodies or your genes are adapting to. So one has to be extremely careful not to lose track of challenging our minds and challenging our bodies. This is something that's extremely important for healthier generations of future beings, human beings and beyond. And the other thing is, well, a very, very careful assessment of the trade-off between quality of experience and the amount of data that you're willing to share. There is no doubt in the fact that the more data you share about yourself, better will be your experience. But given that to enhance your experience, a lot of apps need a lot of data about you, you at times end up sharing more data than is needed. This makes the developers lazy because they know that they can get all the data that they want and more, so they don't really see what is the data that they actually need. So moving forward, my word of advice is that when you try to make use of technology that is being made available to you, look at the price that you're paying in terms of giving your privacy up. Each app, each technology capability is higher experience only if it knows more and more about you, but there's only so much that it needs to know. So two things that you have to be careful about regarding privacy: one is how much should you share, and secondly, what is being done with what you have shared. Is it discarded, destroyed, absolutely made unavailable to anybody else the moment it's used, or is it lying somewhere in this huge mesh of computers in the globe that it can be accessed by somebody else, either with malintention or in well, of course, trying to make profit out of your data is also malintention in some sense. So please always be careful. Do not share more data than you need to for the level of experience that you need. And two, make sure that you know what is being done with the data that you share with the entity that is providing you with the service. So with these words, I want to end by saying that 5G as it stands today is only the beginning. The way you're going to see the world in the next few years is going to be magical. A lot of you youngsters who've not seen the transition from the 90s will find it hard to believe that it's magic, but believe me, the way the technology is building, even you will start feeling overawed by the changes that you will see around you. So these are good, happy times, but we have to be very, very careful about how we give up our privacy, how we leverage, how we continue to be masters of the technology and not become slaves of it. Thank you. I'll be happy to take questions if any.
Thank you, sir. We will go ahead and take some time for questions now. Just a reminder, please be sure to type your questions into the question box in your control panel. So it looks like we have two questions. Both the questions are from Vinti Nair. So Vinti Nair asks, the first question is, thank you, Professor, for the illustration of the application of 5G as a game changer. What's your vision for 6G, sir?
Yeah, so like I said, thank you for that question. Yeah, so let me take one question at a time, Mudassir. So thank you for that question, Vinti. Yeah, so because this was a 5G talk, I did not spend too much time on 6G, but there were a couple of things that I did mention. I strongly believe that in 6G, there'll be a lot more consolidation. 5G has been ambitious and it holds a lot of promise, but not all promises will be delivered, as always happens. So 6G should be about making sure that the gains that we've promised in 5G are delivered. And of course, because it has to service the globe for the next 10 years following 5G, it should also have technologies which are faster, lower latency, more concurrent. So those kind of network performance characteristics is a given, but it will be primarily about consolidation. It will be about ubiquity. It will be about a lot more uh, you know well, not participation, but you'll see a lot more AI ML in your network. The machines will take more and more control of your network and also the applications. So you will see a lot more of AI ML around you, and 6G will enable shared experiences and immersive experiences to the next level. Mudassir, the second question,
Yeah.
please.
Thank you, sir. Second question from Vinti Nair only. Sir, what initiatives in AI ML is your research pursuing?
Okay, so now, like I said, 5G is about making communications happen. AI ML is about handling data. The data could be sensed, the data could be generated, and making decisions, recommendations, processing the data, identifying patterns, and then either actuating certain devices or providing feedback to the human. So in AI ML, you see things happening at the network level and also at the application level and also in the cloud when you're doing where your data resides. So in our group, because we look at two aspects. One is application, where we look at computer vision and NLP very carefully. So that's one area where we're going to apply AI ML, and I'll talk about that shortly. And the other area where we're trying to leverage AI ML is in the network resource allocation and network experience, well, rather user experience enhancement by optimizing network parameters. So in the second area, what we're trying to do is see how AI ML can be used for finding out techniques for enhancing optimized user experience end to end. So all the hops in the connection from one endpoint to another, how do you ensure that the quality of service is enabled and delivered? So AI ML will take decisions at different points along the route. It will take decisions on what level of service to deliver, and it will keep monitoring whether or not that level of service is being delivered. In case it is not possible, it will either inform the network to make corrections or inform the user that it cannot be supported. So it is going to make your life easier by way of managing resources of the network. The other area, of course, like I said, is in the application layer. So at the application layer, what we're trying to look at is one, in computer vision, we are trying to improve the way you represent the videos and images. Today, you have two mechanisms of actually two independent activities that you need to do to make images useful. One is a compression technique and the second is a tagging technique. So you have tags and features that you need for searching, and you have compression to make sure that you're able to store and transmit. But in our group, what we're trying to look at is the next generation of AI ML based compression, where compression is description based. So when you have a representation or a compression technique which is description based, it enables both search and the fact that you reduce the amount of data that you need. And there is a third thing that it enables. The third thing that it enables is it enables AR, VR. It makes it very easy for objects to be introduced in the scene. It makes it easy for objects to be removed from the scene, and most importantly, it allows for synthetic scenes to be generated from the modeling data that you have represented using description. So that is one area that we are looking at. We are trying to repeat the same thing for speech, because speech again is about searching, because you want to search music, you want to search a certain speech, you want to look for certain keywords and find answers, and you also want, on the other hand, to compress. Compress for storage, compress for standardization, or for whatever else. So there again, we are looking at a description. And when you have descriptive based methods, what happens is that it is very easy to combine modalities and include context for better recommendations, because speech is descriptive, because a video is descriptive, and context in any case is a set of rules, or rather data resulting in a set of rules. You combine the two modalities because they are in the same space, add to it the knowledge that you have from context, and come up with better search results, better recommendations, better inferences, and the like. And finally, we are looking at AI ML for the next modality that is gaining a lot of ground, which is haptics. So well, a combination of e-skin and the pressure that your joints and muscles exert for making certain activities happen. So that's pretty much what we are doing. Thank you.
Sir, we have, it looks like we have few more questions. So Pamela Kumar asks, do you have any specific AI ML project in the 5G test bed?
Okay, so in the 5G test bed, there are the ones which are under deployment, development, and some under design. There are 2 or 3 of them. I'll talk about 2 of them. One of them is haptics, where we are trying to leverage the capabilities of MEC and those of AI ML to understand what the human is trying to convey to a robotic hand at this point in time, and a robotic arm eventually. So you have a robotic arm, so you are trying to do teleoperation. So you have the haptic glove on the one hand, so you have a user. The user is located at a remote location, and you have an arm and a hand which is trying to do dexterous activities with the objects in the actual scene. So there we need a lot of AI ML in ensuring that these two understand each other without any lag. So we have AI ML in representation of the data on both sides, and we have AI ML for predictions in case the link between the human and the device breaks. So this is one area we are looking at. The other area that we're looking at for AI ML is enhanced experience in gaming or sport events. So if you have multi-view cameras and some of them moving on rails or UAVs, how do you, based on the context of the user and the background history of what the user likes seeing, and based on the action in the field, how can you provide a very personalized video stream to the consumer? So every client, or sorry, every viewer will see the game in the way that he or she wants to see it, not that the game result will change, but the angles from which you will use it. When do you see replays? When do you, what commentary do you hear? What at what times do you pause? What part is recorded? What part is not left for eternity? What images are clicked? All of that will be done using the AI ML capabilities. And the third AI ML activity that we are trying to do by leveraging the 5G testbed is is precision agriculture enabled by UAV. So the idea there is that you have a UAV that senses the condition of the plant or the crop, and based on its conditions decides the amount of irrigation. So it decides on the amount of pesticides, and it decides on things like the yield estimation. So precision agriculture, where you will use concurrent connections because of large number of sensors that you'll deploy, and high bandwidth and low latency for the UAVs that you might have flying to cover fields to look at the crop rather than individual locations on the farmlands, will be combined using AI ML to come up with not only recommendations for the farmers, but also information for insurance agencies, for people who trade in crops, and for the government to regulate. Yeah, thank you. I hope that answers the question.
Thank you, sir. We have two more questions from Rakesh Mehrotra. The first question is, Professor, please talk about data security and its misuse in 5G and 6G environment.
Okay, so now data. So there are issues related to 5G with data security, and there are issues with data security even without 5G. So we will focus only on the issues related to security because of 5G. Now, because of 5G, what is happening is you are connecting more and more devices to the network, because you want a massive machine type communication things to happen. You have a lot more devices which have access to the network. A lot of these devices are low end, so they are easy to hack into, and if you can hack into these devices, you can hack into the system, and therefore play havoc with it. So one area that one has to be very careful. So there is already talk of what we call security by design, because you know that endpoints today are going to be very, very vulnerable. So 5G is focusing on endpoints, especially the low end endpoints, being what we call secure by design. To give you an example of how this happens, when you look at a vehicle, you build a very, very secure network for V2V and V2I communication. But then what you realize is that there is almost no security inbuilt in the way the sensors connect within the car. Now, if that network is not secured, and it has no encryption and other security measures, it's easy for an intruder with malified intents to enter the network through that car and then play havoc with not just the car but the rest of the system. So while the 5G is trying to make the network connection secure, unless these endpoints are also strengthened and hardened, it will be very difficult to ensure security. The other thing that you must be very, very careful about is the fact that soon you will have a lot more capability on your handset. Your devices will become even more attractive and capable. And when they become more capable, they offer you more services. And the moment they start offering you more services, you have to start sharing more and more of your data. They start collecting data about what you've been doing. There could also be things like audio always on to listen to you, so that you get the right kind of recommendation at the right time. We don't know what time Alexa stops listening to you, just we under the guise of providing you enhanced service. But so that's the other place we have to be very, very careful. So while those endpoints, the weaker endpoints are going to be secured by design, the humans will play a huge role, because a lot more of them will have a lot more capable handsets in their hand. It becomes their responsibility that they share information about them and about their environment and those around them carefully. What good is ensuring your security and privacy if one of the members in the group has an always on phone and he listens to all your conversations? So you've had a very, very effective use of your phone, but somebody in your group does not. That is as good as everybody being compromised. So these are two areas, the two most obvious areas of security breaches that are becoming possible. And as I speak, people are already looking at ways to plug these gaps. Thank you.
The second question from Rakesh Mahrotra is, what measures are being taken for ethical practices and data monitoring?
Ethical practices and
Monitoring those things, in 5G or 5G test bed.
okay. So now, the moment you talk about ethics and monitoring, you get into the domain of government, because um, ethics is something that the society decides. Okay, so so talking about ethics, uh, and in the same tone talking about the ill medical effects, if any, within quotes. I'm not saying that it is bad for health, but assuming that it has bad, those are decisions that are taken not at the technology level, but rather at the government level. These are decisions that have to be taken by the state. Is it willing to mine at the expense of environment so that it can power its industry? So that's a call that the technology to extract coal from the earth cannot do. All that the mining industry can do is have the least impact on the environment, but the environmental impact is a given. So that is a decision that is taken by the government or the state, and the same holds for monitoring. What a human can do individually is what I just talked about in the answer to the previous question. But for making it non-leaky, to make it foolproof, what you will need is uh, regulations from the government, regulations that ensure that people do not make mistakes, such as leaving their recommender on while talking to other people, not allowing app builders to, for example, have this kind of a capability without, for example, speaking out every few minutes that you are being heard, just as you have those displays of you are under electronic surveillance. Those kind of things cannot be done by technology alone. These have to be driven by the state. But you're very right. These are very real fears, and they should be tackled by the government. And the government should also play a role in a third area, which is policy. And policy comes even before regulation. And so policy should be driven by ethics, and based on regulation it should correct its policy. So eventually you should have a policy and a regulation in place. So the TRI and other regulating bodies have a very important role to play in these times of very quickly improving technology.
Okay, sir, we have one more question from Pamela Kumar. Are you planning any contributions to standards?
Right, thank you for that question, ma'am. Now, I will take a slightly circuitous route to this answer, because this is for the people who dial in. Uh, Standardization is driven by two things. One is a requirement, and two is a technology capability. So for making contributions to the system, there are two kinds of things that need to be in place. One is comprehensive, believable studies of the requirements of the people that you're trying to service. And secondly, you should have enough reliable, proven technology so that you can participate in standardization. Standardization is a very tough game. A lot of players spend billions of dollars in building tech, and they want most of their tech to find its way into the eventual standard, even if it leads to a non-optimal solution to the requirement. But if you have a strong technical footprint, you can become an important player. So to answer that question specifically, ma'am, we are planning to contribute to standards. Two areas that we are looking at very carefully as we speak are, one, there is still work happening in the space of broadcast. So the group is exploring how to contribute to broadcast, and for that we are looking at protocols at the link layer. We're looking at some processing that we might need to do based on the quality parameters that we read at the physical layer. And there's also some work that we're doing in the transport. But the idea there is, how can all of this be put together and be put forward for standardization effort. The other effort that we are trying to do is for a little more futuristic technologies moving towards 6G. Like I said, AI ML is going to play a much stronger role. So the group here is exploring 2 or 3 areas of AI ML and participate in standardization. The first standardization effort that we are going to do is in the area of advances in MEC as we move towards 5G and beyond. And there we are in the process of writing a study item, trying to push it to make it a NIP. So these are 2 specific areas of standardization that we are contributing to. The other 2 areas are representation of speech and that of video, and a generic technology area that we are looking at right now is QoS/QoE, which will find its way into some specifications for the current and future standards.
Okay, thank you, sir. Then we have a question from Neeraj Nore.
Just a quick check, Mudassir.
Okay, okay.
Are we going as per schedule? Because I think this talk was till 8:45 or something.
No, we are going to wrap up this now, your talk, sir. So this question has already been answered by Mr. Asif from TSDSI, and then Rakesh Mehrotra is suggesting us to please read the book by Rajiv Malhotra in AI to take care of pitfalls. Okay, Rakesh, we will try our best to read this book. Okay. So thank you, sir. Is there anything else you want to cover before we go ahead?
No, I'm fine. Thank you very much for listening to me. I hope it was useful to give you the perspective of what's happening and what we are doing here at IIT Delhi. But the real good stuff is to come now. So now please stay on and listen to the 2 actual works that we've done as part of the 5G testbed initiative at IIT Delhi. One on MEC, the other on baseband processing engine. I hope you benefit from those 2 presentations. All the best. Have a great day today. Thank you. Bye-bye.
Thank you, sir. We will go ahead now, and we are unable to connect Professor Huzur Saran sir. So I will go ahead and we will go for first expert talk, which will be on multi-access edge computing, and is given by Professor Arzad Alam Khirani. So I will give a brief, coverage of what is multi-access edge computing, what will be covered by Professor Arzad Alam Khirani. So multi-access edge computing integrates the service provider's network with the high performance computation facility to cater to various applications such as augmented reality, vision applications, at the network edge, thus reducing the overall latency and preserving the bandwidth to send the complete data to the centralized data centers for processing instead. This MEC testbed simulates various MEC entities and components, integration with 5G core, sustained by an application deployment use case. So the following topics will be covered in this talk: a high-level introduction to MEC and its applications, ETCI architecture of MEC, implementation details of MEC in the testbed, a live example of application development for the audience to understand. So let me give a brief introduction and bio sketch of Professor Arzad Alam Khirani. Professor Arzad Alam Khirani is an associate professor in the Department of Electrical Engineering and Computer Science, IIT Bhilai. He is also an adjunct faculty with Bharati School of Telecom Technology and Management, IIT Delhi. Professor Arzad Alam Khirani completed his ME and PhD in 1999 and 2003 respectively from Indian Institute of Science, Bangalore. He is also a co-founder of Adverse Technologies Private Limited. His research areas include broad areas of computer networks, queuing systems, wireless communications. He also worked for industry for a decade and gained experience with product conceptualization, product design and development, industrial R&D, and standardization. So we welcome Professor Arzad Alam Khirani now. Welcome, Professor.
Hey, thank you, Mudassir. And thanks, Professor Lal, for the excellent opening remark. Now what I'll do is I'll share. I guess my screen is shared already, right? Okay. Alright. Okay. So the topic of this discussion is basically to update you on our approach to development of MEC system or indigenous 5G testbed activity. There are many contributors to this system and to this development. So I have tried to provide a list for the same. As you are aware, Professor Saran is the PI for this project and Professor Lal is co-PI for this project. I from IIT Bhilai have been working on this. Professor Maithili from IIT Bombay and Gaurav Shukla, who is at IIT Delhi currently, and Sushila, Ashish, Vinod, and the team. So all of them have made significant contributions to this development. And today in our agenda, what we'll do is, because we want to uh, help you understand how to write MEC applications. So you may have heard a lot about MEC. And if someone has, let us say if someone has given you an MEC system and you are wondering how to write an MEC application, by end of this discussion, after myself, Gaurav, Ashish, and Vinod have presented our work, I hope that you will be convinced that it is very easy to write MEC system applications, and you are always welcome to try out your ideas on this 5G testbed MEC system, integrated MEC system. This system is ready right now for trying out third-party applications, so you are always welcome to try out your applications on this. I will not be motivating a lot about MEC because I mean that's not the objective of this talk. So this talk is more about architecture. So I'll briefly talk about what are the considerations that we have to keep in mind when we are designing an MEC system and integrating it with a cellular system, right? So the basic motivation for MEC system comes from this kind of figures. So this is a concrete use case where you see a control room where you have lots of such TV panels, and there's a lot of surveillance feed coming into each of these screens. Right? Now imagine this room being manned by a person, and that person's responsibility is to detect some events, which are maybe say crowd builder and so on. So first of all, this monitoring this kind of feed will require someone to be continuously looking at each and every feed in parallel, right? And then as soon as something happens, that person is required to raise an alarm. Now, obviously, this sounds very impractical for one person to be able to do it. So either you employ many personnel to be looking at each and every such feed. But the problem is that most of these feeds do not have anything happening for most of the time, right? So events which are kind of interest to in this particular case would be very rare. So first, so you get many questions. Why can't we just automate them for increased reliability? Because a person relying on a person who is just staring at these screens continuously will certainly lead to boredom and we miss any event. And also, what is the need for sending all this data to a control room? Why don't we just have intelligence at some kind of edge where, so that's why edge comes in. So that's the emphasis on edge, where some amount of this processing is already done about what should be sent to the control room. And then only, so this edge acts as a switch. When some event is detected, that edge sends the, opens the switch, opens the gate for the traffic to go to the control room. Otherwise, it is silently just looking at that data, right? So what is the capability of this edge devices? So here is one example. If we were to do that incorporate that kind of intelligence at the edge, so there are different definitions of edge. Edge can be a very subjective term, right? So when we talk about edge, the first thing that would come to mind is the edgest edge in some sense, which is like the last edge, which is the end device itself, right? So you look at this camera, which is a solar powered camera, and it is a cellular connected camera, right? Now, this device, it has been installed at some location. So in this particular example, it is hooked up to a tree, and you will see that many such camera will be installed, and assume that most of them are giving this live feed. So first of all, if you incorporate such intelligence at this end devices, then certainly the cost of this end devices will go up. Second, management will go up. The management of such devices will be very hard, especially in terms of upgrading the software whenever you want to have a redefined, let us say if you have some event which is defined in software that these devices are capturing, and if you want to add to that list, or if you want to make some changes to that particular logic, you will have to do an over-the-air upgrade of many such devices, right? So that's a management challenge, and obviously the cost is very high. So this is one example. Professor Lal has talked about many such examples, and so again, my objective right now is not to motivate NEC. This is just an example. So what I'm trying to do is motivate what qualifies to be an edge, right? So here comes edge computing. In edge computing, essentially what we have done is we have right now seen that somehow maybe at the end devices you cannot have all the intelligence. And also you don't want all the intelligence to be at the end server, right? So which is the cloud server or the data center. So there's some place in between where this data can be tapped and processed. So that's what is called edge. Even now, even with this slide, the notion of edge is not clear. I understand this is slightly vague even now, right? But what is it that the edge would be doing? The edge would be providing some kind of basic analytics, some caching, and some machine-to-machine enable some machine-to-machine communication locally, possibly if you do not require that communication to go to the data center. So things like this, and you can keep on adding to the activities that edge performs. Right? Now, many of us have heard about many confusing terms and related terms: edge computing, cloud computing, fog computing, and all. I will not get into the details of what is the differentiation between them, but just please keep in mind that they are different. So right now, that's all I would say to limit the scope of this discussion. And there are many people who have clarified this difference between cloud computing, edge computing, fog computing. Okay. So now we come to the main topic of the discussion, which is about understanding the edge in the cellular system. So remember that we are talking about a 5G test bed, right? So this is a cellular system, and we have to define what is an edge in a cellular system, in such a cellular system, when we have to implement our edge computing platform or edge computing service. So to be able to understand the definition of edge in such cellular systems, let us just look at how applications talk with each other. On the left side, you would see a typical Android framework. So this is Android architecture. Some of you may have some familiarity with this kind of architecture, where you have Android telephony layer, and then you have vendor rail and Android rail. So RIL stands for radio interface layer. So vendors do provide their own rails, they do their own modifications and provide some customized services. But overall, what happens is that you have this applications running on the phone. So right now I'm just talking about phone, but this discussion is general, right? So any application running on the phone which requires data connection talks to the underlying layer, which is basically connecting this application to a cloud server or an end server via IP addresses, right? So effectively, what we know is that there is an IP address assigned to the phone or the interface here, and then there's an IP address assigned to the server, and one of them is either having a public IP address or they have they're using some kind of net traversal and so on. Whatever that the case may be, the routing, the connection is established using IP addresses, and that's all we know. So if the source and the destination know the IP addresses of each other and the source and destination ports, then everything in between is considered as a cloud, right? So that cloud is basically doing the plumbing between the these applications, say XYZ application on the left side to the cloud server on the right side, or the server end server on the right side. So in this, how does cellular communication come in? So in cellular communication, you can actually think of a base station before the cloud. Okay. So here I am giving a hardware level example, or equivalent of the previous slide. On the left hand side, I'm just showing the hardware that goes into a phone. You have application processors and where the applications are running, and the 4G or 5G modem, right? This modem are actually connecting to the base station, which could be your 4G, 3G, 4G, 5G base stations, right? Then this 5G base station or 4G base station is connected to the end server, right? So this is the cloud. We have now introduced the base station before this cloud in the previous slide. However, there's something more to this cloud now. And please bear with me for this slide, and here the details will be clear. You get something called operator core network. Okay, so whole of this complete story can be now broken into two smaller clouds. The bigger one that you see on the right side is the public internet. The smaller one that you see the middle of the slide is what is called operator core network, okay, which is completely managed by operator, and that is not necessarily IP based. That may or may not be IP based. It runs all kinds of proprietary algorithms and protocols. So only thing is that what comes out is basically a data connection from this operator core network, right? Now this operator core network varies across technologies. So we have seen in 2G there was different kind of core network, then 3G, 4G, and 5G. So when we are talking about edge, effectively we are talking about being closer to the base station. Okay, so when we are talking about MEC in cellular communications, we are effectively talking about doing compute while being closer to the base station. Hence, considerations around the operator core network become very important. We need to first have a good understanding of what is the operator core network, and then see what are the possible ways in which we can integrate our MEC system with this 5G or 4G core network. Okay. So let us have a brief look at how operator core network looks like in 4G systems. So this is also called EU term. Some of you may be familiar with this architecture. So at the end, you have something called user equipment, UE. The base station is called E node B in LTE, which stands for Evolved Node B. And then you have something called service gateway and PTN gateway. Okay. So for us, the operator core network is essentially this cloud, S gateway and P gateway along with E node B. It would be a good analogy to say that the PTN gateway is effectively an extended version of your network interface card for the UE. Okay. So you can think of whole of this as one system and just say that PTN gateway is my network interface card. That's all. And that is what is connected to the external network. However, what has happened is that because this particular architecture was frozen long back, actually around 2007, 2008, and MEC concepts became more important later, around 2012, 13, 14. So this architecture was not very ready for a direct integration for something like MEC. So there are approaches available to integrate MEC systems with 4G networks, but they are very complex. So one of the, and there are many approaches available. One is called bump in the wire, where you basically start tapping. So tapping and then so this is a GPU tunnel. So you actually tap into this tunnel and then decrypt the packet, and then process it, and then encrypt again, and then send out. So that is not a very clean way, but people were able to do this. Okay. In the case of 5G, fortunately, things are better, because 5G was already taking MEC into account, and the people who were pushing MEC were also participating in 5G and ensuring that there is good support for such offload available in 5G networks. So here is one example, one architecture diagram for 5G. You may see many variants of the same figure. Left side is again your end device, and right side is DN. So DN stands for data network. So that's what you can assume as representing the internet. Okay, and please remember this N6 interface. I think you will see hear about this N6 interface again and again when Vinod also talks about it. And the most important entity from our point of view will be this UPF. Exactly the way that you are able to view this PTN gateway in 4G network as an extended network interface card. Here we can do the same with this UPF, user plane function. Okay. So in case of 5G, the operator core network cloud corresponds to these entities, and the data path is shown as shown in this yellow line. Okay. The clean thing about 5G is that you have a very good clear tapping point for attaching your MEC host to the system, and that is what can be done via this N6 interface, as you can see in this image, where I have just now added the MEC host. Okay. So this architecture details are something that Vinod will clarify. Now, what happens to MEC applications? When we are talking about applications, do applications need to be aware that they are using MEC? Yes, they will need to be aware, because they may be explicitly talking to MEC applications in between. Okay, and this is something that Gaurav and Ashish, when they tell you about how MEC system is implemented, and they will also run you through one example where you will yourself be able to develop an MEC application today itself while the sessions are going on. Okay? So you will realize how easy it is to write an MEC application and modify these applications. So overall, the flow, so this is a brief flow overall what happens in MEC systems, how a client application is able to communicate with MEC system is like this. Someone has written a client application which wants to use MEC application, and there is a device application that we have provided. So we have the MEC service providers, let us say. So the left side is still the end device, which is your smartphone, which wants to use MEC application or MEC services, for example. The device application will act as a proxy between this client application and something called user application lifecycle management proxy. Okay, so we don't have to remember all these details, but at a high level, the reason for having this kind of UALCM layer is that we don't want to expose the complete mobile operator system, so MEC system, directly to device applications. So there's some proxy which is required in between. And when we come to the players in this ecosystem, we'll see who owns what. Okay? So I'll talk about that in a minute. The flow goes something like this. Client application requests device application will now talk to ULCM, which is going to now talk to the MEC system, which is integrated with the operator core. Okay. The MEC system's responsibility now is to talk to the 5G core, and they together will identify the best MEC host which should run this application. So this is something that Ashish will possibly talk about, where we are implementing this, and there is a patent also that he is writing on this for the 5G testbed, where we have our own way of selecting the hosts. So there can be many such hosts available in the system. Okay. The appropriate host that we want to connect this client application's MEC application to is it requires some logic. So that's what I think Ashish will also talk about. Now it is possible that this MEC host does not have the corresponding MEC application which can serve the client application. Okay, so the objective is that in this MEC host there should be something running which is serving this client application, right? So it is possible that when this client application has requested, this MEC host did not have that application. So this will fetch the application. Enough information would have been provided to the MEC host to fetch this application. It will go get the application, and once everything is done, the client application is given an indication that now everything is fine. IP addresses and everything is fine. You can now talk to MEC host. Okay. So this is the control plane part. Once we have done this, once we have achieved this, and you will see what it requires to achieve this. Okay, so Gaurav will walk you through many such slides where the details of each messages will be discussed. So once this is done, we are all set. Now we have all these communications possible. So the client application can directly talk to the cloud server. The cloud server can also interact with the MEC application, which is running on the MEC host. The client application can also talk to the MEC host or the MEC application running on the MEC host directly. Okay. So we have to, so when we come to the model for this system, so who owns what? So from point of view of an operator, it may be a very messy business to be owning and managing MEC services. Okay. So one model would be that there are some app providers, there's an operator, and there are many small MEC service providers. Okay, so whole of this ecosystem looks like will be sustainable, because there will be many small players. They will have their own value-added services and so on, and they will provide MEC services, while app providers will be separate, right? So, this is what we feel right now, that we will have three kinds of players in this market. So overall, this is more of a acknowledgement slide and thank you slide to other participating members who have helped a lot in this integration. So the entities involved in this integration activity were IIT Delhi, IIT Bhilai, CIVIT from Chennai, and IIT Bombay. So IIT Bombay was responsible for the 5G core UPF part. CIVIT has been doing a lot of work on 5G core plus RAN emulator part. So RAN is the radio access network. And MEC system and applications have been developed at IIT Delhi. And we from IIT Bhilai have been working with IIT Delhi. So this has been a very, an excellent effort, and during COVID time, we were able to integrate this completely while having all these online meetings. That was a very a great achievement, and I thank all the participants and the developers in this activity. So you have already seen such lists, I guess, many times. So I will just quickly go through them. You can do MEC applications include real-time video analytics, Internet of Things, virtual reality, and so on. So here I'll pause for a minute and move to another slide, which has been shared by IDRBT, which is Institute for Development and Research in Banking Technologies from Hyderabad. So they are actively looking at MEC use cases, and they have defined such use cases for us. So we are also talking to them. These slides are from Dr. Abhishek Kapoor from IDRBT. But this is a list. All that I would want to convey is that, so you can see that there's a list that people working on banking technologies are looking at for MEC. I will not go into each and every MEC application mentioned here, except that this one, the first one, which allows dynamic creation of meeting rooms for secure audio video conferencing between the bank staff and the customers. So that this is one vision of IDRBT, that they think that we will be able to leverage MEC system to achieve this kind of, or to implement this kind of service, and also being able to do this kind of opportunistic video analytics, where the live feed from ATM and branches go via MEC, and they do some amount of analytics. Right? So that's the kind of use case that banking sector is also talking about right now. And obviously, so here I have just given a high-level analytics. Those were the concrete examples. Now let us look at what other operators in the world think about MEC systems. So this is a view that Verizon has put up on their webpage. This is very similar to what we have seen. So I hope now that you are convinced that our view of the 5G MEC system is similar to what others in the world are thinking about. So you have these end devices which are thin client, they are low cost, low battery life, and so on. And there is an edge, so 5G edge, which is delivering mission critical low latency applications, or it is serving such applications. Similar view is also shared by AT&T, and they do emphasize the virtualization architecture also here. So our MEC system will also have virtualization architecture. Right now it does not support it, but we are incorporating that. This is the MEC architecture that has been proposed by HC. So HC is a European standardization body, and they have been very actively pushing MEC integration with 4G and 5G. This is so you will see this image, this figure again in Gaurav's slide, where he will give you this information in much more detail. At a high level, what I can tell you is many of these interfaces. So this is UE application, the application running at the end device that we have seen. This is the ULCM, the LCM proxy that we had discussed. Many of these interfaces are actually REST API calls, nothing more than that. Some of them are very tightly standardized and detailed. Some of them require our proprietary handling and our proprietary definition also. So we have done such definitions. Not all the interfaces are well defined. Okay? So this is one point that I wanted to bring out in this when I'm showing this slide to you, that not all the interfaces in this architecture are well defined, and the MEC system developer has to incorporate or define those interfaces. So that is what we have done, and you will see in Gaurav's and Ashish's presentation how we have done it. The HC recommended 5G MEC integration is summarized here. As I had already talked about in the 5G core architecture, core network part, we will be interfacing. We have decided to interface a 5 MEC system via the N6 interface, okay, through the UPA. So that's the summary of this slide. Details will be given by Vinod. Vinod is an expert in the 5G core network, so he will be talking about those considerations. So with that, I will stop, and I will hand over the presentation. I'll request Vinod to take it forward now. Roughly, the idea is, or the flow will be this. Vinod will present the 5G core aspects that impact the MEC integration. Then Gaurav and Ashish will explain the MEC architecture, which has been proposed by HC. Then they will be giving details of our integration approach to 5G and 5G integration. So now I'll hand it over to Vinod. Thank you.
Am I audible?
Yes, Vinod,
sir.
you are.
Yeah. Thank you, Professor Assad, for an elaborative explanation on the MEC subsystem. Good morning, everyone, and myself, Vinod from CIVIT. So like currently a part of the 5G testbed project, working on the 5G core and currently part of the 5G testbed project, currently working on the 5G core development and the 5G RAN emulator development. So in this session, we'll be discussing about how 5G core and 5G RAN emulator combined together provide an end-to-end 5G test platform for MEC integration part. So agendas for the today's session will be like to go over all the 5G core components that is available in the indigenous 5G testbed. So all the core components and the basic introduction about the same, and also an overview of the 5G RAN emulator, and like what are the capabilities of the 5G RAN emulator and what and all tests can be performed by the 5G RAN emulator. And then we'll be looking into the MEC setup overview. So how 5G RAN emulator and the 5G core setup combined together form an end-to-end connectivity platform for an MEC integration, and how the MEC components got integrated into the setup. Gaurav will be talking extensively on like how MEC level interaction and communication will be happening. And then we'll be looking into the AF traffic influence support. So how exactly a trigger from an MEC subsystem is handled within the core, and how the user plane data has been rerouted from like an cloud DNN to an HDNN kind of thing. So the 5G core, which is part of the indigenous 5G testbed project, is like jointly developed by CIVIT, IIT Bombay and IIT Madras. And so this is fully it is based on, it is compliant on release 16 of 3GPP specification, and also it is fully based on the service-based architecture, and it is REST compliant. So the NF that we have in our 5G core subsystem are AMF, access and mobility function. So AMF is key responsibility NF, which is used to handle the registration and the connection management functionality, and also it handles the mobility and UE location related services. Next is like unified data manager management service NF. So this is like an aggregator for managing all the user subscription information and other details of all the user network related informations will be handled by the UDM. Then we have UDR, Unified Data Repository. So this is like a data repository which is part of the 5G subsystem, which will be used for storing all the user subscription information, exposure details, and also the policy information. So all the structured data that will be like taken up from the 5G core subsystem will be stored in the UDR. The UDR is used only for storing the structured data, and since all the it's like follows a REST principle, so every NF is like totally independent kind of thing. So no context or any information will be stored in any of the NF. So we have a separate NF called UDSF, unstructured data storage function. So where an unstructured, like all this context information, everything will be stored in the UDSF. Next we have PCF, like policy and charging function. So this is basically a lighter version. So the implementation goal for PCF Lite is more on requirement driven kind of thing. So based upon each of our like let's say like when an MEC subsystem came in, so we took up all the requirements that should be addressed by the PCF, and only those components has been developed. And also like for normal session establishment, other things. So basic call flow procedures and basic traffic influence support, all these basically the PCF Lite development is more requirement driven kind of thing. Next is like network exposure function. So network exposure function is a gateway for the 5G core to communicate with the external subsystem. Basically, NEF is an which exposes the network capability and other information to the third-party server. Let's say when an untrusted AF or any MEC orchestrator or any kind of MEC application, external application function, if they want to communicate to the 5G core, it will be via the NEF. So NEF handles like both security handling. So basically like information that is used within the 5G core is more it will more like a protected kind of thing, like a basic UE identifier and other thing. So which is only known within the core components. But for an external entity, so it will be more like a generic public subscriber identifier kind of thing. So the major functionality of NEF is to convert the information received from an external entity and to convert into a format which the internal core NF can understand. So this IE level translations, everything will be done by the NEF, and NEF will pass on this communications to the other NFs. Apart from that, it like let's say an external NF can subscribe saying like for a particular UE location. If the UE moves from one cell to the another cell, please send me a notification kind of thing. So an external application can register a subscription event with NEF. And here NEF has an intelligence to know that which NF is responsible or like which NF has this particular information. So in this case, the example that we have taken, let's say that external application want to know if the UE is in mobility kind of thing. It moves from one cell to the another cell. So the external application will do a subscription request to NEF, and NEF will register an event with AMF saying for this particular UE, if it moves from one cell to another cell, please send me an event. So whenever an event happens, AMF will send a trigger back to NEF, and NEF will notify the external AF. So in this way, like the data that can be exposed from the 5G core to the external entity is like more controlled by the NEF subsystem. Next is NRF. So NRF is a network repository function. So NRF is a network repository function. So NRF is like a key component of the service-based architecture. So whenever any NF comes up, let's say AMF comes up, UDM comes up, so these NF register itself with NRF. It's more like a telephone directory kind of thing, where any NF that comes up, it just stores the information saying like, okay, I am up and these are my profile information. And whenever let's say like if now NEF got an subscription request saying like for a UE location change, please send me an event. Now NEF need to know for this particular UE or for this particular UE which AMF I need to communicate to. So it can go and send a discovery request to NRF asking for, I'm looking for an AMF that is catering to this particular SUPI or a particular UE. So based on the data that is available within the repository, NRF will select the AMF or like a bunch of AMF that matches the criteria and sends the response back to NEF. Now NEF will use this information, and based on that it can communicate with the corresponding AMF. So NRF, it serves as a network management function which stores all the profile informations of the NF, and also it supports a discovery function. Like if any NF want to discover the based on the service, if I want to discover any other NF, it can use NRF, send a discovery request, and based on that it can find that particular NF kind of thing. So next is the session management function. So session management function like supports all the session related functionalities, like a session creation for a particular UE, and also like session creation, release, delete, and the mapping of this all this QoS and other parameters for that particular session. And also it handles like configuring the user plane path. So and all this current NF that is available in the 5G core of the 5G testbed, whatever we are discussing now is part of a control plane entity. So as I said, SMF will handle all the session related attributes and creating session, deleting session, checking the get fetching the corresponding session policy from the PCF, saying like what and all flow descriptions can be received from the for the particular session, and based on the rule set, it will configure the user plane path. And next is like an authorization and selection function. So AESF is like a prime enough that is used for the UE authentication in the home network. It uses UDM and UDR to run all the encryption algorithm and other thing. But the AESF is like a UE authentication validator functionality kind of thing. So these are the core NFs that is available as part of the 5G core subsystem. And next is, as I said, so this is part of the control plane. And then via an N4 interface, SMF will connect to UPF. So here UPF is our data, it will be in a data plane. So user plane function, which is basically like will route all the user data to the corresponding data network. So in this case, whenever a session establishment happens, now like let's say a user has registered to the network, now I would want to send some data, it will try to do a session establishment. So it will try to send a session establishment request, which will be catered by the SMF. Now SMF will be requesting PCF for a policy set for this particular session. So PCF need to give the corresponding SM policy information. This SM policy information will be having all these packet filters and the other QoS flow descriptions and other information. SMF will impose this information via, so this the underlying protocol under N4 is PFCP protocol. So SMF will put in this policy in the UPF, and based on this traffic flow packet filter information, UPF will redirect, like handle the incoming traffic that is coming from the UE. And also like AMF connects to a GNode B, an access network via an N2 interface. Underlying protocol is SETP, and also GNode B connects to the user plane function via an N3 interface. The underlying protocol is GTPU. So in our 5G core, which is part of a 5G system, all these NFs are in place, and also the stacks like stack to communicate with the GNode B at the control and user plane is also in place. Next we will see about and next is like based on this packet filters. So based on the packet filters provided, all the QoS information, so the SMF will be giving the UPF in case of packet descriptor rule. So it can be like a forwarding action rule, buffering action rule, or a QoS enforcement. Basically like the UPF, it is just a blunt data forwarding entity, which primarily works based upon the rule sets that is provided from the SMF layer. So it takes in all this forwarding action rule and QoS enforcement rule. Based on that, incoming traffic from the UE. So basically user mobile will be connected to GNode B, and once the data flow happens, so UPF will do all the QoS enforcement, and all this packet filter rules will be applied on the corresponding packet. Based on that, it will do an N6 routing. So N6 routing is not basic IP based routing, which will be connecting to any external network. So based on this packet filter, now the UPF will know to which DNN the data should be forwarded to. And so again, the DNN can be like a default internet gateway, and we will be having multiple DNAs as part of our internet gateway. Like for example, like let's say for this particular conference or this webinar session, if we have a separate server that is hosted in the DNN in our internet gateway, that will be having a separate DNA, which is like a separate domain name for that particular application kind of thing. So next we will look into the 5G RAN emulator part. So as part of 5G testbed, we have developed the 5G core, and we needed a testing tool to validate this 5G core component. And this the requirement for the 5G, like a development, the main driving force for development of the 5G RAN emulator was like it should enable, like I should be able to test my code both on the procedure level and data load level, and also to enable an end-to-end pipeline for an external user to come in and test their data or like test their application. Let's say like RAN emulator will emulate a UE and it will emulate an access network. It will try to connect to our actual 5G core. Will do all the control plane. So based on the configuration provided by the user, it will do all the session establishment, registration, session establishment, everything. Data pipeline will be created based upon the user requirement, and the user can use like this particular end-to-end pipeline to send in their data packets. Like an application can be integrated to send in the corresponding data. So this is like an overall like a block diagram for RAN emulator. So RAN emulator, we have like a well-built UI subsystem, which is based on both CLI, command line interface, and also we have a GUI to control the RAN emulator component. Here the user can give a, like based upon his preference, he can configure their subsystem accordingly. So he can like it can emulate around like max up to some 10,000 UEs, and hundreds of Gnode Bs. Emulation is possible, and also the user can do like multiple test mode support is also available. So as a user, once I take up the like when I want to configure RAN emulator for my application, so he can configure like what slice I need to use, or if I want to take up a separate slice for my like separate data flow and other thing, all this configuration can be made, and he can provide in number of Gnode Bs and number of UEs that need to be emulated. So based on the input provided by the user, the controller will try to emulate those many numbers of UE. Let's assume an example saying now user want to emulate 100 UE and 1 Gnode B. So 100 UE emulator stacks will be spawned accordingly, and also corresponding access network stack will be spawned. So in the UE stack, which is part of a UE emulator inside the 5G RAN emulator part, the NAS is fully spec compliant and it is compliant to release 16. So that is like for the core network, the N2, N1 and the N3 interface, everything that is coming from a RAN emulator is spec defined. So it will be transparent for the 5G core, whether it is connected to an actual RAN access network or it via a RAN emulator kind of thing. And similarly, this NGAP, as I said, NGAP, this N2 interface is also fully spec compliant kind of thing. So we are spec compliant up to release 16, and towards the core, it is totally transparent, whether we are connecting via an actual access network or via RAN emulator. So based on the user input, they will be spawning those many UE threads. The UE will be emulated. Similarly, like access network will be emulated if it is like if you want to do a Gnode B access network, and also it has a support for a non-3GPP network support, where I can even spawn an N3WF, a part of a RAN emulator, and can connect to core as a non-3GPP UE connected via non-3GPP access. So so this is an overall overview of 5G RAN emulator and what it can like can be done kind of thing. So next we will see few ability of the 5G RAN emulator. So one is like I can do procedure level testing, like registration or any 3GPP call flow can be tested. User can do can emulate any kind of scenario. Let's say like I can, as user, I can emulate a real-time scenario. User comes up, there is like an RLF radio link failure is there. Again, user is coming up, and how my end-to-end application is going to handle it. And we can do a data load test either via an external entity, or else we have an inbuilt traffic generator to handle it. Signaling load test, as we discussed, like I can create 10,000 UE trying to register to a core, and application test. So in this session, we'll be more discussing about the application test, where RAN emulator and core together will form an end-to-end 5G testbed pipeline, where a UE comes up, registers with the network, creates a session, and the data pipeline will be enabled for the application to take up, and application can use this pipeline to transfer the data. Similarly, from the control plane perspective, any AF can communicate to the 5G core via NEF. So okay, we will be discussing about the call flow in the forthcoming slide. And next we have an error gen support, where user can emulate an error at an IE level, saying like if for any kind of registration, how my application is going to handle kind of thing. Any error gen is supported in the RAN emulator part. So how RAN emulator and the 5G core constitute together to bring in an end-to-end 5G setup for testing this MEC application. So RAN emulator, so we will be spawning. So this is basically for an application test. So RAN emulator will be acting as a UE. So RAN emulator will be registering. Let's say it will register itself with the network, create a session, and the end-to-end data pipeline will be readily available for an external application to take up and route the data accordingly. And there are like multiple options that are possible via which an external in this case, let's assume an MEC client app can communicate with the RAN emulator. So either the MEC client app can be an internal application which is running along with RAN emulator in the same PC. So currently, we are working on addressing on the control plane path also. As Professor Assad was saying, there is a vendor rel. So this vendor rel will pick up this application data, convert into corresponding AT commands, and will pass it on to our connection manager inside a UE stack, and the modem will process that particular command. So that is under development. In the current setup, what we have, all the control plane entities will be handled by the RAN emulator. So UE comes once the user starts the RAN emulator, the UE registration happens, session establishment will be done. So the end-to-end data pipeline will be created accordingly, and it will be left open for a use like an external MEC application to start pumping the data via the dedicated tunnel that is been as data pipeline that is been assigned to that application. And there are like multiple options that is possible, like user can run their MEC application within the same subsystem, or even like I can use some kind of like a Raspberry Pi kind of thing I can run in an external machine to forward the data into the subsystem, because like it is basically just a normal IP packet routing. So a TUN interface will be created for that particular session. So any like application data need to be rerouted to this particular TUN, and from the TUN the data will be passed on to the access network, and from access network via N3 GTP tunnel the data will be passed on to UPF. So based on the control plane aspects, let's say as a session is created, a basic policy will be taken. So based on that, the packet filter or the packet detection rule will be applied on the corresponding incoming packet, and based on that it will be forwarded either to like an via N9 interface, like towards the next UPF, or directly towards a central cloud or a DNN cloud DNN kind of thing. So this is the overall MEC setup with 5G RAN emulator and 5G core. And within the MEC application interaction, so how my MEC client is going to communicate with the UE lifecycle application management, and how my MEC host and orchestrator is going to communicate. So all the interactions that is going to happen within the MEC subsystem will be taken up by Gaurav. So that is like a continuing session post this. And so AF traffic influence. So actually this is the 3GPP call flow that is being used to support the MEC subsystem. So basically a traffic steering happens. So based on an event from a core, a control trigger will be initiated to like steer the UE traffic. Now, okay, you need not send to the cloud DNN. Please redirect all the traffic to the edge node. So this is the basic call flow that is gonna will be happening. Let's assume like now our 5G core component is up. Let's say all the NFs are up. It registers with NRF. my 5G core subsystem is ready. So SMF will like to by default do some default PFCP configurations to the correspond, like the PFCP link will be established to the corresponding UPFs. And once an MEC, so let's assume like UE registration, everything happens. Now the data pipeline is set up for the MEC client application to pass on the data. So now once a MEC client application sends the data via GTP interface, the RAN emulator will be sending the information to a ULCL UPF. So ULCL UPF is nothing but an uplink classifier UPF. So what it does is it is more like a splitter kind of thing. So based on that, it decides what is the next hop of UPF that need to be like to which the packet need to be sent kind of. So once the packet reaches ULCL UPF, it redirects to the cloud UPF, and from cloud UPF via it will be sent to the cloud DNN. So this is the normal data flow that is happening. Now the MEC subsystem, once the edge node is up and there is a requirement for the data redirecting towards the edge node. So the MEC orchestrator, which is an application function which will be interacting to a 5G core, will be sending an 3GPP AF traffic influence. And all this communication, as I said, is via service-based interface, as we discussed in our first slide. So every NF will have its own all the service endpoints defined. So it will be more like HTTP nef.5gc/ and the URI is defined as per the 3GPP. So 3GPP has defined a mechanism how the root API should be, and that information will be available with the MEC orchestrator, in this case an AF. So using that URI, so AF will send that 3GPP traffic influence. So this will be having like all the packet filters information, like which particular application data we need to reroute into the edge node. So let's assume like only one application is running, so which is our MEC app is running in our let's say in a mobile phone, only one application is running. The corresponding packet filters for that application will be given by the MEC subsystem. So this will be having, so this information like this is my source IP and this is my corresponding destination IP, and if any of this, and also port, so it is like a 3-set tuple kind of thing. So if any of this combination matches, please reroute to the corresponding edge node kind of thing. And then we will be having the UE IP address information and also the GPSI. So GPSI is nothing but your generic public subscriber information. So it will be like an UE at domain name kind of thing. So which is like a global identifier for that particular UE. So for these particular UE, please imply these are the packet filters that need to be applied at the UPF. So once NEF receives this information, now NEF need to translate this information. So because the internal 5G core NFs will not be able to understand what is the GPSI. So what NEF will do is it will communicate with the UDM, the subscription database, will convert this GPSI into an MSISDN. So MSISDN is nothing but our mobile number. So once that is done, NEF now will send a PCF authorization to PCF Live, saying, hey, I got a traffic influence request from an external AF. So for this particular UE, for this PDU session, so IP address will be used to identify the particular PDU session, and the GPSI will be used for identifying the GPSI, and this is the packet filter set that is being provided. Now PCF will check its policy database, saying like whatever provided by the MEC orchestrator is valid or not kind of thing. So again, everything is based upon subscription, and everything will be like under the like an umbrella of a charging function. So whether the MEC subsystem is first enabled to cater this particular or use this particular kind of edge node or other thing will be validated by the PCF. In our case, everything is done via a configuration file. So a pre-filled configuration file is shared between the core network and the MEC subsystem. So the information will, the policy and other information will be synced across between the external AF and the 5G core. Once the policy, okay, well, now the request that is given by an MEC orchestrator is validated. Now PCF will convey to SMF saying, for this particular UE PDU session, please apply this packet filters. So SMF will select the corresponding, all the selection of UPFs will be done. So what edge UPF I need to use, ULCL and cloud UPF will be done. And it will convert this packet, what is the packet filters received into PDRs, into a packet detection rule sets. Like it will put it as a source IP, destination IP. Just it's more like a normal a packet filter tuple kind of thing. So that information will be passed on to the edge UPF. So once that is done, whatever UE packets that is coming to a ULCL UPF, once it matches to this particular PDR, it will forward all the packets to the edge UPF. And from edge UPF, it will be routed to a corresponding HDN. So this is how the basic the traffic influence call flow that is like handled within the 5G core subsystem. So this is basically an IP flow that is being handled within the subsystem. So so initially, when the IP packet is being originated from the UE application, so the source will be like the UE, and it will be addressed to your MEC end server. And once it reaches to the G-Node B, so G-Node B will do a GTP encoding. So since the entry is via GTP tunnel, so basically GTP is nothing but IP tunneling. So we have an IP packet and we encapsulate it over one more IP packet, in which the source will be the G-Node B IP, destination will be the ULCL IP. So now based on the PDR packet filter rule set, now the ULCL will decide, okay, let me just, now it decides the next to hop. So I need to forward all this application data to cloud UPF. So it changes the outer IP structure. So the destination IP here will be changed to cloud UPF. So once a packet here comes to the cloud UPF decodes, do a GTP decoding and will pass on the application data to the cloud DNN. And once the earlier call flow, whatever we saw in the previous slide, MEC detects an event saying like, so the event can be anything. So currently it is, in our case, it is more an user triggered event kind of thing. So the user is deciding when to do it. But the event can be eventually anything. So whenever an MEC orchestrator feels like, okay, now the data should be rerouted to the edge node, the traffic influence call flow will be initiated, packet filter will be given, corresponding packet filter will be applied in the ULCL node. So now what happens? ULCL, once it receives the application package, it detects like, okay, now I need to redirect this packet to an edge UPF. So corresponding external IP set will be modified and data will be sent to edge UPF. And from edge UPF, packet decoding will be done. GTP decode will happen, and the basic, whatever the application packet that is originated from the user mobile will be sent to the corresponding edge DNN. So within the edge DNN is where we are running all this MEC host and other subsystem, which Gaurav will be handling. How this data exactly is handled within the MEC subsystem. Yeah, so by this we have a very clear picture of like how an 5G RAN emulator and 5G core together forms an end-to-end testbed, 5G testbed pipeline, creates a data pipeline and paves a platform for testing this MEC application. That's it from my side. If there is any questions, I can take it up.
Sir, we don't have any questions yet, but it was an excellent and very informative presentation. And so you can switch to Gaurav, and then we will see whether we have any questions or not at the end.
Sure. Thank you. Asif, can you please connect to Gaurav?
And then I'll come into the picture. Then I'll present the live demo of the MEC file and all the. Hello. I think Ashish will share the some PPT of the architecture that we have and how we have implemented that. And there afterwards, I'll be taking care of the MAC 5G testbed to give a real demo of the MAC 5G testbed of the application development. So is Ashish there?
Yeah, I make him presenter right now, Mr. Ashish.
Yes, yes, I will start presenting now. Thank you very much, Asif. Okay, just a minute. So we'll take forward from the discussion which Vinod has talked about the 5G core, and now I will go on the details of the implementation of the MEC system. So I will discuss the implementation detail, and later on Mr. Gaurav will present the demo of the testbed. So in application deployment in MEC environment, we have three levels. One is client and edge level and the remote level. So the applications which requires the high computation and very less latency, they will be deployed and executed in the edge. And for the cloud, if it is beyond the limit of the computation at the edge level, it may be served from the cloud. So MEC host usually deployed at the network edge, which is part of the MEC platform, and it has the compute, storage, and network resources. So now we'll go to the functional design of the MEC system. So we'll discuss about the MEC components, which will have the MEC entities, MEC and MEC interfaces, and the information flow among the MEC components. So to give a more idea about the MEC entities and components, so we have already seen in the previous discussion about the UE, UALCM, and Vinod already talked about the NEF, PCF, SMS. And now here our main focus is on the MEC system. So we have the MECO, we have which will have the MECO DB, and it handles the various registrations, and it will connect to the MEC host. And there are various other entities like MEC platform manager, MEC application, and ULCM, and RAN emulator, which already Vinod has discussed about. So in MEC system, we also have the MEC interfaces, so through which we connect to the various components in the MEC system. So we have the system support interfaces designated by the MP, and we have the management interfaces, which are designated by the MM interfaces. And we have the external reference points, which are called as AMX, like it will connect within the UE and ULCM. Within the MEC system, we will have the MM interfaces. So in this deployment, we have used the MP1 interface, which and we have used the MM9 interface, which will connect the MECH and MECO. And we have the MX2 interface that will connect the UE and ULCM. So now this is the complete idea where we have integrated the UE with 5G core, and we have the MEC system. So first of all, if a UE will initiate the app context, after that that will be processed by ULCM, which will forward it to the MECO. Then MECO will get the UPF and UE info and select the appropriate MEC host, and MEC host will come with the traffic rules for redirecting the traffic to the MEC host. Then this will be again passed back to the same channel using ULCM, and then UE will contact to the UPF, and via UPF the data will be sent to the MEC host for the processing. So in our system, we have 7 virtual machines. So that one machine is RAN emulator, other is 5G core, ULCM, and MECO, MECH is the MEC host, and server is the where we divert the traffic, and then it is a cloud server. In 5G setup, we have created the several virtual Ethernet in the VMware to create the internal data network for the MEC system. So this will give one idea about the overall setup. So this is the RAN emulator, and the RAN emulator is connected to ULCM via MX2 interface, and then it is connected to the MECO via MM9 interface, and then MM9 interface is connected to the MEC host, which is deployed in the edge data network, and it may have the multiple MEC hosts. Then the 5G core is connected, will have the ULCL UPF and edge UPF. Cloud UPF is on the separate machine, and then it will connect to the cloud DNN. So with the app level details, the UE will request to the ULCM to get the list of app available, and then MECO will revert back and return the app list. After that, UE will request for the context creation, which will be handled by the MECO, and it will come with the information of the MECH, which will run the app. And after that, once the application is finished, the context will be UE will create a request for deleting the context, and then application will be completed. So this is the API level details now. So the API root is the URL of the server where we will have this this interface running. So this app list will have the list of the app which can be utilized or which can be called, and then we have the request post request with app context parameter. Then client app will give the put request, and then once the application is completed, the client will give the delete request. So this was between the client and device app. Then the both client and device app will be running in the ULCM. Now device app will request the ULCM, and then ULCM will request the MEC system. The request and response is like based on the reference point which we have created. So MEC informs the 5G code through NEF and shares the UE ID tag for traffic subscriptions and receives the info related to the 5G code. At the time of life cycle completion, MECO sends a request to MECH for the running the app in the platform, and also keep the record of registered MECH and ULCM. So this is pretty much on the flow of the application. Now integration with the 5G core. So this part is already covered earlier, so I will skip this part. And also Vinod has covered this already, that how we are going to connect to 5G core with the MEC system. So this is our single. So we have earlier have our implementation with the single UPF implementation, and later on we have integrated with the 3 UPF implementation, where we have the ULCL UPF, Edge UPF, and the Cloud UPF, as Vinod has already described about it. So now our system has this shape, where we have ULCL UPF and Edge UPF running in the 5G core, and we have Cloud UPF running on the separate machine, and MECH, that is the MEC host. Now I will quickly move on to the implementation detail. So we will go through the list of the API design, then JSON message, and various details of the endpoint reference point which we have created, and the database design. So we have database at MECO and MECH. So MECO database is responsible for handling the various registration requests of the MECH ULCM, and MECS database will have the traffic routes registration, and it has the DNS rule registration and various parameters of the app and app list. So MECS registration will have ID, type, IP address, port address, status, system info. ULCM registration will have also the similar information. Then the context registration will have context ID, app instance ID, callback reference, UE, IP port. This is important for running the application, and this information is used by the MECO, and MEC host also use this information for checking the app. Then traffic rules registration. Then we have the various parameters for the DNS rule registration, that will have the app DID and DNS rule ID, DNS rule, and the timestamp. And the MECO database will also have the app list, that will have the vendor ID, app's name ID, app DID, app description, app characteristics. So that will have the details about how much memory it will require, and how much time it will require. So we have also have a set of JSON messages which will be interchange between the entities. So I will also go with this. So this is the MEC architecture document. So this has the whole implementation details. So we have this messages format. So an app list will have this following parameters, that is app name, app provider, app soft version, and app description. So this is from this is the app list, and app memory, storage, and latency requirement, bandwidth. Then we have the app context. So the input message will have the app name, app soft version, app D version, app package. So this is the app information regarding the application, and we'll receive the response like this. Then for updating the context, the JSON message will be having the app ID, then the callback reference. Then software version, D version. Then for traffic registration, we'll have the traffic rule that will have the filter on the flow. Then this will be the IP address, source IP address, destination IP address. Then we'll have the source, destination port, etc. So this was for the registration. Then we have this for the DNS register. So we will have the DNS rule, and we have the IP address, time to live, and we'll have for the traffic rule. If there is any update, we will pass the app instance ID and traffic rule like this. So we have designed the various API at the various level, at the various components, that is ULCM, MECO, MECH, device app, client app, MECH platform, and 5G core. So we'll go by ULCM first. So as we have already seen, there was the find app list. So this is the reference point which is being created at the ULCM, and the interface used is the MX2, and the method which we'll be using is the get. So ULCM receives and accepts the request of the UE and get the app list. Then ULCM also have the create context reference point. So it will be between UE to ULCM, and it will receive the post request from the UE to create the context. Then it will also update the callback reference from the UE for the UE. It will be created from the UE. So ULCM receives and accepts the put request along with the context ID of the UE and forward request to the MECO. Then MECO will also have a reference points like this, where this request will be forwarded. So then UE will create a delete context request to the ULCM. So ULCM receives and accepts the delete request, and ULCM along with forward request to the MECO. So there is also separate request for registration from the ULCM side, and this will be sent from the ULCM to MECO for the at the MM9 interface. So ULCM sends the post request with the ULCM header, which will consist the properties of the ULCM, and it will receive the response back from the MECO. Then this is the request which will be forwarded from the it will actually initially come from the UE, where it will request for the find app list, and ULCM get this request with ULCM and UE header. ULCM receives the response from the UE MECO and returns the response back to the UE. Then we have the request to MECO from the ULCM to create the context with the following reference point. And ULCM sends the post request with ULCM header, which receives the response back from the MECO and send it back to the UE. Then ULCM send request MECO to update the callback, and ULCM returns the all responses back to the UE. Then ULCM also have the request for the delete context to the MECO. So now at the MECO, these are the following reference points which have been established. So this is on the MM9 interface, and this is for the MECH registration. MECH receives MECH sends a post request which will be received from the MECO, and it will process and enter the registration detail in the MECO database and sends back the response back to the MECH. MECO will also perform the ULCM registration, where it will receive the request from the MECO, which will request from the ULCM, and it will again reply back to the ULCM and enter the registration details in the LCM registration table. So this is the find app list request received from the ULCM. So this is the create context which we already discussed about, that it will be received from the ULCM to MECO. Then this is the delete context request which will be received from the ULCM to MECO in the same sequence, from UE to ULCM, then ULCM to MECO. So MECO receives the response code, and this will send the response back to the ULCM. So this is the request received from the ULCM to MECO on this reference point with the context ID. The MECO updates the new callback reference with the context ID in the database and send back the response code 204 to ULCM. MECO send request to the selected MECH and for the context deletion. And once it is a response, it sends the forward back the response to the ULCM. MECO will confirm the context will confirm the context information from the selected MEC host for after the context creation, and will receive the response code with the app instance ID with which the app is going to run on the MEC host. So this is the function for the MEC host selection. Then MECH receives the request for it will send the request to the MECH for the context confirmation, and then MECH sends the request for the MECO for the context deletion. So this is the app traffic rule registration that will happen between the MEC app and the MECH. So app sends the registration request to MECH, and it will have the traffic rules in the database and return the response code after updating it. So this is the request for DNS registration. So all the DNS related information request to the MECH, and MECH inserts these rules in the MECP database. So here is a traffic rule by app instance ID and the traffic rule ID, and at the MECH. So MECH will return the updated rule once it receives this request. Then app sends a request to get or put the DNS rule associated with an app instance ID, and MECH retrieves the DNS rule and update with the response. Now app sends the get DNS rule associated with the app instance ID, and it receives the DNS rule and it will send them back. So there are few more reference points which are created on the device app. So in the device app, we have the create context request that will be received from the client app to the device app, and it will forward it to the ULCM, and here it will also receive the delete context request. Device app will also have the update context request and receives the event notification callback reference. So similarly, we'll have few more requests on the client app, so these are the requests which client app will send it to the device app on the Amex 2 interface. So this is the request for the app context creation. Then similarly, it will have a request for the delete context. And for traffic rules, it will have the to MECH by MP1 interface. Then at the MECO, between the MECH and MECO, there is a request for the traffic rules, and MECO will return response back to the MECH. So these are the requests, and MECH platform will have the event notification request. So this will be between the client app to the, this will be the message to client app via device app. So for the event notification, and at the 5G core also there are requests for the traffic influence subscription. So this all APIs we have implemented in our testbed, and we have all the reference point we have created. So these are, as we have discussed, a lot of API design. So for that, we have all these API correspond to either app list, app context, and MECP registration and LCM registration. That is a life cycle management related information. Then for the app instances, and the other part is app traffic registration, where we'll have the traffic rules and DNS registration. And furthermore, we have the various API related to the event notifications. So in our implementation, we have the implementation framework on the Python Flask, and we have created the virtual machines. So we have two setups. One is in the IIT Delhi, and other is in the IIT Bhilai. In IIT Delhi, we have the VMware, and in VMware, we have created the 7 guest machines and instantiated all the MEC components. The MEC application is developed as a client app, MEC app, and the cloud app in the corresponding to the details, and it has the communication between the client app and the device app. So MEC app also have the onboarding and instantiation, where we'll have the fetching the app instantiation, and back propagating the application info to the client app. So we will demonstrate object tracking application where objects in the frame will be tracked, and the based on the count received, or based on the video received, the count will be calculated at the MEC host, and based on this count, if there are a lot of people in the frame, that will be forward to the cloud, demonstrating that the scene is of high importance, having the large number of people. And if it is having a few information, it won't be forwarded to the cloud and it will be processed. So this way we leverage the edge by not sending all the data to the cloud, but limiting based on the processing at the edge. So this is a video will be streamed from the cloud, from the client side, and then it will be coming to the MEC host for the processing, and then based on the computation, it will be forwarded to the cloud or not. That will be decided on the MEC host. So after this demonstration, we'll see the case study of the app deployment, where we'll specify the client app, the changes in the client app and the device app, and how we can configure the MECO ULCM and instantiate an app on the MEC edge. So I will want to hand over to the Mr. Gaurav so that he can demonstrate, and later on I will come back and demonstrate the MEC host selection and its importance after the completion of the demo. So I will request Asif to please make Gaurav, Mr. Gaurav as a presenter.
Yeah, Mr. Gaurav is the presenter right now.
Okay,
And
so
so unmute his video also, camera.
hello. So my machine is visible and I'm audible as well. I think. Can somebody confirm, please?
Yes, sir, you are
Am I
audible
audible?
and presentation also visible for us. If you can
So
unmute your camera also, sir.
actually, I don't have a camera. I'm actually sitting
Okay,
on the workstation.
problem. Yeah, no
I'm
problem.
working on the workstation, not sitting on the work. So that doesn't have a camera here. So either so that won't be possible. But I'm audible. That hardly matters.
Great, sir. Thanks.
So anyways, I need a full screen view also. So because I have to write the code and all that. So welcome here. So I'm Gaurav Shukla, a part of MEC 5G testbed. So this is the architecture that we were referring to. So what this architecture is about. So this is a 3 UPF virtual machine setup here in MEC 5G testbed. So let me show you how we have implemented. So if you can see, this is a RAN emulator here. So this is one machine RAN emulator. This is one machine 5G core. And within the 5G core, there are 3 applications running. I mean, one of the 5G core, there are several components of 5G core that are running in 17.132, whereas the ULCL UPF is running on 17.134 and Edge UPF is running on 18.160. And then there is a cloud UPF which runs on 17.135 and transfers the data to the cloud DNN, which is server, to 0.10, and the Edge UPF connects to Edge DNN. Similarly, we have MECO. So MECO is the one where we were referring to as an application function, and MECO will send the data to the NEF. So NEF will connect. So traffic subscription will be sent from the here to from the application function to the 5G core. So now let me show you what this virtual machine is all about. So we have a virtual machine here. So this is RAN emulator. This is a 5G core. This is UPF cloud. Okay. So this is the UPF cloud application that is running. So I'll show you how the data is transferring from RAN emulator to UPF cloud and to the edge also. This is our MEC orchestrator. And then there is MECH, which we can call it as MEC host. So here the application will be residing, and one of the MEC platform application is running here. And then we have ULCM, ULCM running here in this machine. And then we have a cloud DNA where the different applications which will be handled which we directly connect from RAN emulator or through MEC host or through the RAN emulator. So this is where all the application will run. So so this is, if you see the architecture, this is the RAN emulator and this is the cloud DNN. So as Professor Azad has described in his earlier slides, once the connection is established, we can connect from RAN emulator. So the UE can connect directly to the server as well as to the edge. So all the applications are running. Right now, I'm not showing all the making all the applications up again. I'm just showing how they are interacting with each other. And with time permits, later on I'll up all the applications, how they communicate, how they bring up themselves, and how they communicate. So let me do one thing. So this is RAN emulator. So from RAN emulator, if I ping to this is cloud DNN now. So if I ping to cloud DNN, you can see the ping is happening. So ping itself is an application that is calling the cloud DNN, the server, the cloud server in fact, and the ping is happening. And now in the 5G core, this is our ULCL UPF. This is UPF. So now you can see the packet transferring from here, ULCL UPF, while edge is silent, edge is not, there's no functioning. So actually it is going to the cloud DNN. So here you can see the packet movement here, and then you can see, then I go to UPF cloud, and now you can see the packet movement here also. So from the UPF cloud, it's reaching to the server. So if I say sudo so you can see all the okay. So you can see the packet movement here also. So this is how now this is the this is a packet movement from DNN, and then I can is called to the, this is the edge server that we are referring to. So we can also call the edge server. So packet movement now here in the 5G core, you can see the packet movement is from the edge server now. So you can see the packet have started coming to the edge. So this is UPF ULCL. So ULCL will transfer it to the edge, and it will start coming from the edge to the this MEC host. Okay, so this is what the ping. So we can directly connect to the cloud DNN as well as the MECH, MEC host, or the application that is running in the MEC host. So I just stop a bit. Now I start an application here. So I run an application. So one of the application that is running is I go to Let's show 3, 4, 5. So you can see the application is running here. I run the server here also. So server application is also running. Like you see. So now the UE has started relaying to the MEC host. So now you can see that this is MEC host. If you can see, now the video that has been streamed from the UE is coming to the MEC host. Okay. So you can see that one of the, I mean, this is myself there. So I am being recognized as number one or the Gaurav Shukla there in the machine. Now the data will not relay till to the server till the I am there. But as soon as my colleague Shashwat will appear on the screen, the data will start moving to the server. So this is where the computation, we are doing the computation at the edge now. So we'll wait for a minute or so, and then it will. So all the packets now you can see the in the 5G core also you can see all the packet movement here from the edge, not from the cloud. So you see the cloud, you can't see a packet movement. So now the packet have started moving to the cloud. Sorry, to the edge. Now I have moved. Now Shashwat has come. So the packet have started flowing to the this server machine. This is the cloud DNS. So it should come, actually it is RTP frame, yeah. Now the Shashwat has appeared. So this is how it is happening. So all the computation that was required to get the phase for getting the phase detected is done at the MEC edge, MEC edge level, which is MEC host by the we called it. So now the server, the data is moving to the server. Once Shashwat phase is detected, so here the UE is relaying the VLC media through the VLC media. This thing the video of the face, and here the MEC edge level it face being detected. Now again I have that's repeating actually. Like this, cancel this thing. Now I show you, this is the RAN server. So here you can see this is the device application. You can see all this, the attributes and the interfaces that we were referring to in the architecture document by Ashish. These are visible. So these are the data that the data flow takes place between device app and the ULCM and the MEC. So all the logs being generated, so that you can see at this level. So contact associated UE app ID, all this thing data is flowing between back and forth between device application to ULCM to MECO to MECP, the platform application server. So this is it. So this is our current setup, where this is 5G core, where what Vinod was referring to. So you can see the visual form of these here only. So this is NRF, AMF, USF, SMF, UDM, UDR, PCF, NEF, and of course important UPF edge and UPF ULCL. So these are the components of the 5G core. These are running in one interface, 17.132, where this ULCL, UPF, and at UPF are running in, I mean, 17.135 and 18.160. So this is the diagram of this. Okay, so you can see this 5G core is running here. UPF you have seen in other interfaces. This is cloud UPF. This is server DNN. This is MECH, and so how traffic infra subscription is in. No, I just in case this is running, I can write a new application and how to. So I'll refer to this diagram actually. How we application development. This is application document. So how to develop a new application. So one of the idea was to show that how convenient it is to develop a new application within the this MEC ecosystem that we have created. So an application there can be divided into three parts: client application, MEC application, and the cloud application. So UE level, edge level, and remote level. So what I'll do, I'll develop this application in front of you. So one of the part is client application, one of them is MEC application, and one of them is cloud application. And so this is, and how the connection has been established between them, how they connect to each other, and what are the various, this will cover this will also be get covered, all of the app list and app context, how we manage this thing. And this is fully automated process. So once you send the app list, you get the context back, you get the app list parameters, then you send for a request for the creating a context and how the context gets created, and all this will automatically there within the. So how easy it is to develop an application, that I'll show. So right now, this is the device application running. This is our RAN server that is running. And we have here, okay, so I open a new application on this. So I create a new application here. So this is the client application directory where we are keeping all the client applications. So I create a new directory, mkdir client. So suppose we create 789 application. We go to client 789. Now I create an application. PIs, let's open editor, and I create application. VI keyboard extraction client. So let's I give you a scenario here. So I am developing an application which takes some strings from the input as an input and passes it and picks the keywords for agriculture domain. So and that will be a TCP connection here. So what I'm doing, I'm just writing a program here. So let me do import socket. So I'm creating for the creating a socket. I'm importing the library for the socket in Python. So this is all in Python. And then system, I would need system command. import. I don't think import RE will be needed. And then we have import time just in case needed. These are the basic libraries that we have to. Now here we will get a reference URL. Means reference URL is basically where we are getting the connection parameters to the edge server. So we'll get something like an IP and a port to the edge server. So we do one. We then we have. Okay, so I have to split it to get the UE. This IP and parameters. So reference URL. So this is so this is it. So I get this value host is equal to temp. So that will be stored in the temp 0 and variable, whereas this port will be stored in temp 1. So now I have this. So now I create a socket for this client is equal to socket dot af inet inet and system. So socket dot so this is for creating the socket, and then after this connection, make a connection to the this is host, and this is so I have to cast this as integer. And this is port. Okay. So the connection is being done with the edge server. Then we have this try for so to take this input while true text is equal to, so I'll get the input from the user. Okay, and then I have this once I get the user, I get that input from user, I can send it to the server, I mean edge server to be precise. Okay, so this is it. This will send, and I have to catch this exception also. Okay, so here I'm catching this thing. Just and at the end, I close this connection. So what this application does is it takes our reference URL as a parameter, splits it, breaks it into host and port, and then takes an input from the client to the connection that has been established between the IP and the port that is has created. So that is in fact the MECH. So this is our keyword extraction line. Now I move to the H server. So here all the processing will be done. So I do one thing. So here there's in this directory I create another application. So this is our H server. So MKTI 789. Okay, so here I keyword extraction. Okay, spelling is right. Okay, this is we call edge.py. So here I am creating again writing this application. So it's a slightly bigger one. So I quickly type it. So this is same import socket. Then import time. Import sys. Import OS and I don't think Flask is needed. Import to song. Okay, fine. So this is it. So now, now I create a. Now this is edge. So this is edge is equal to. I create a socket again. So again a socket dot socket. And this now this edge dot bind. Right. Then we have this again. We have to do the same thing. So here we get the this IP and port as system arg. So I just simply write system.arg v1, and then we have sys.arg v2. Okay, so here I have to port it as integer, cast it as integer. So there here. Okay, so and then we have so we really need two brackets. That's okay, fine. So and then we have as dot listen. So listen how many lines it can listen to. Let's give 5. And what I'll do, I'll get the here list from a a file that is there. Okay. Okay, AGR list is there. And so I open a file. So I get the current working directory from the where the MEC application MEC platform is running, and plus app store. The application is app store. Mm, 789, and then we have this agr underscore date dot txt. Okay, so this is it. This is we read the file. Of course, in a read mode, so I have to write here read mode, and that's all. Line by line is equal to my file. So my file, I open this file and read it line by line. Read line. Okay. So is my screen visible? So I can zoom in also, just in case you prefer. So file and line. So I first convert them to lowercase, so lower, and then words. So they are all separated by comma. So my line dot is split. And then I separate them with comma. I split all the pass them all the words separated by comma. Okay. So then, so for each element in words, I simply dot r strip. I remove backslash n. So these are the standard things that we do when we read the file. And then we have here this. So we'll store it in the variable now. And yes. So then again I read my line equal to dot read I. So this is done for reading the line, and then I close the file. So I read from a directory there. I read from a file agr.txt dictionary.txt. Now, now I create a. How much time are we left? So my def. So I create a function send to cloud. So uh, this will pick all the uh, keywords all the keywords to the cloud. So cloud, here we have this, again we have a one socket connection to the cloud. Socket stream. Used for this connect. So suppose our application is running on some, this is IP of the 0.10. This is the IP of the server that the application is running, and we have this suppose okay, okay, so this is the port. Suppose we are running an application on 8448 port, and we have so now this is the client. We have created a client for, so for EL in keywords. So we get a list of keywords for EL in keywords. EL in keywords. Client dot send EL. And then I can close this connection. And close. Okay, so I have put. Now, in order to read this, true. Now this is listening from the this was for sending the cloud. This is for listening the. Okay, this is. And so here we have used the variable edge as looking. So edge pay that's the length. That's it. And this is from client. I'm using. And then again while true. Just quickly. Save, and here we receive some 096 bytes, and then we have if not data, then break. Okay, so okay, fine. So from client we can restore this data variable here in the client variable. And then we have words. Uh, okay. I don't think we need this thing. We can do it. Or we have this demo. Get another list. Yeah. Real words. So I break each and every word and then assign it to EL in. So I check it with the list that is there, AGL list, whether it is there or not. And then if it is there, EL is equal to bring it to lowercase. And append it in the temp directory. Okay. Temp dot append. Okay. Here. So there we know. If so, one is condition we have to put, if length of the variable is 0, means there's no one, don't send it to cloud. Then send to cloud. So this is it. And then we can close the connection. So that's all. So all the computation, that's a bigger, slightly bigger program because all the computation is been done here. So this is our and last but not the least. Uh, I go to the server. So I can start here. So I just server, so somewhere in the server, this keyword extraction server, or so we can say cloud is ready. .py. So we have this again import socket. So this I'll take another 5 minutes to type it down, and then we can start building the application. Import socket, import sys, and okay. So we can say client is equal to socket. Yeah, fine. And socket string. This keeps appearing. Okay. String. So by this is where your, so we can say 192.168, or we can say here we can run it as system on one as integer arg arg. Okay, so this is it. No, I'm just missing something. Two more brackets. So try true text raw sorry text raw. So import server socket string client dot connect. Here we have to use, so this is actually cloud, so we use this cloud here. Cloud dot cloud. This is cloud. Okay. So we have to bind it with this thing. So while true, we can have action we self-protect. Then we have, again we can run while true. We not have this thing. So server.accept, and then we have the while true data that should not receive mm, 096. You can open here. And then we can have a connection close here. Okay, connection is closed now. The connection we are making here, we have to put this inside this one. And I can print the print. Here we can print it. So, this is what we have done. So here, actually, how much time is left? It has consumed too much time. So now what we will do, we run this server script here. So Python keyword cloud 192.168.32.10 and 8448. Here this is the name. Okay, here, okay, this is cloud. So I have similar application here. So this is how we have developed the applications. So one is at the RAN emulator, and so this is where the client is there, and this is where this. So in the client, you can see we have a key, this application here 789. So we have a similar application in 567 also. So we have a similar application in PD 567. So we have a similar application text algorithm, text extraction, text recognition client.py. So it is the same application that we have written. So basically what we have to do, so here you can see this one of the, so in this directory we paste this script here. Then we have a client, so we have a context file here, sorry, client context file here. So here we will simply, so all the parameters, so now all the application, the parameters, the app list and all this context ID that has been shared. So this is done with, is taken care of by this file only. So all we need to do is to replace the code here. So so this is the where from where we are calling this application. Just simply replace this code here, Python text recognition client, and this application will start. So all the parameters are there in the already mentioned in this file only. So if anybody who wants to develop an application can bring the the whole exercise was to show how you can develop your application to 3 different levels: client application, Azure application, and cloud application. So here in the RAN emulator where the UE is running, we can replace this text recognition client, the client application that we have developed here, so by simply writing this line, and it will work here. Similarly, all we need to do is to register this in MECO or in MECO application function. We have to register this thing. So all we need this application. So we have to insert this line, like this is 50567 application that is already there. So we have to simply insert this line for the that attributes that it requires, and what is the FDID of this, which you uniquely identifies, and this application gets registered in the application function, which is MECU orchestrator. So here, and then we have this uh, we have this uh, at the edge level, we have this MEC, we have this config mec.ini. So here we can mention, so what are the commands that needs to be run this application. So we have a script app command like Python, and we have this application text recognition h1.py here. So this is the file name that will run. This MECP application server will automatically translates this into running the application. So it will open an application by running the command Python text recognition h1.py and providing the app parameters that are required. So all the like the server that it will get connected to, and I mean from where the data is coming to, and from where data has to be sent. So this is, it is coming from UE. It will be it will be read here, and it will be sent to the server. And so all we need to do is to change this. So I mean the level of portability of application is quite simple here. So we can build a three different as certain parameters that needs to be taken care of. That is all. And we have this. So here also this application is there. So text recognition. So we have this text recognition cloud here. So this is it. So now I run here text recognition. Sorry, I run here Python text recognition cloud that is running in the server. So suppose when it has to connect to server, if and when needed, it will connect. Then we have this. So I start the application from here. So I simply, now I have a client.sh script. This simply calls the client.context file, and client.context file translates, reads from the parameter file, and that it runs the application as shown in the code. So it is sending, it will open an application here. Okay, so far so good. So we'll get back the, okay, now I have got this, enter the text. So I said this this is the harvest time. Okay, so let's see what's it. So okay, so what it has read, the all the variables that are there in the in its list, and it's checked what are the what are the keywords that were there in the string. So it has picked harvest and time, and it has relayed it to the server. Now you can see the server keeping track of all the keywords that are mostly used. So if I give harvest time again, and showing also some of the parameter agriculture, yeah, and some blah blah blah. Okay, so it will so it will pick all the This time it has picked this harvest time showing agriculture, and it has updated the server. So now the server has been updated to harvest appear 2 times agriculture. So this is the application that see, it took me. I mean, I wasn't. I was running short of time. I wasn't able to debug the code. But the whole idea was how quickly you can develop a simple application and can be deployed in the MEC system with in 2-3 steps only. You just need to enter it into the database, just change the code there that this file has to be run from here, and simply in the configuration file. So this is the whole idea of application development, and this whole document talks about this. So I mean, I don't want to get into this MI app list and all this because this has been covered, and I mean, mostly most of us will not remember this. So you can go to the Swagger and can check it there. What are the parameters there? So you can check it there. So this is the app list parameter that is there, and the traffic rules also are there. So every time application runs, the traffic rules are registered that are also there in the uh, mentioned there in the one of the Swagger here. So these are the traffic rules. So this also get registered. So you can have traffic rules there. So accordingly, you can from within the application you can drop the packet if you want to drop the packet, if you want to send the packet using these traffic rules also, and similarly from the DNS rules, so you can get the from which server you want to connect to. So in this application we have used DNS rules to connect to the server. So this is the idea of a whole I have shown you. Basically I tried to cover, I mean, most of the things were covered in the slide, but I wanted to give you the real picture of how the easily it is, how easy it is to develop the application here. The whole for the webinar. So, I mean, a lot of details have been covered in the slides. So this is some practical example of developing the application, and it will give you a clear, I mean, the real in the in the real scenario how we develop this thing from the what we have what you have seen in the theory. So I think that is from my side. If somebody wants to ask something, and I can switch to Ashish to give a little overview of the host selection. So basically what happens, I just give you a brief about before going to Ashish that uh, what happens when random later calls, it initiates the app, get the app list and initiates it. Then all the list of the apps comes to the random to the UE, and UE again selects the application and sends the create a context for this. So I can run it over the edge. Now when it comes to the edge, before selecting the host, MECOS has different list of hosts there. So which host needs to be selected to run that instance of application? Then it runs certain algorithm. I mean, that is expected. It will have detailed description of the host, and through some algorithmic method, we can select a optimal host to run that application. So this is where Ashish will give a this slight overview about the host selection after this. So I mean, I think we have 15 minutes left for our presentation. So Ashish can cover that in 15 minutes, I think. Hello, Ashish, are you there?
Yes, I can. I am here. So if I can be a presenter, then I can start presenting the host selection. Thank you very much for.
Yeah.
So is my slides are visible now? So I will talk about the MEC host selection.
Yes, it
So
is.
we have seen the Yeah, so we have seen about the MEC system. Now we'll highlight the importance of the MEC host. So a service provider will have this MEC system, that is a computation facility, but they have to place the MEC host with in a geographical location so that it can serve the as many requests, and can also minimize the latency and while addressing the more number of users. So as you can see in this picture that there are client, it can be the ambulance, it can be any device, it can be a mobile user. So they will be connecting to the MEC system, and now there will be the set of MEC hosts, so which will be connected to the UPF. So each UPF will have a certain number of MEC hosts which are directly connected to it, where a computation can be offloaded. So here in this example, say there are 3 MEC hosts, and a doctor is streaming the patient's video he wants to view. So MEC host does the initial level of computation and gives the concrete information so that the processing can be so that the decision can be made faster, removing the redundant data. And we have already talked about AI, ML, and lot of related things which can be employed in the MEC system. So this is kind of an AI, ML infrastructure which can be deployed on the MEC host, and it can give the concrete and strategic information to the doctor to make a clear decision. So there are certain key parameters which are very useful for host selection. So this is like a geographical location of the MEC host, and we have to optimize the resources in the MEC host and minimize the overall latency, minimize the system cost, that is the uh, final throughput which we are achieving. And we also have to plan the resources which are required at a particular MEC host, and number of MEC hosts, because a service provider should know that how much traffic it is going to receive, how much computation offloading it has to perform, and it can quantify it, and based on that it can take the strategic decisions which are key contributors on optimizing the cost of the MEC system. So we have modeled it as the arrivals from the UPF. So each UPF is connected to certain number of MEC hosts, and the arrival will come with certain probability. So for each MEC host, we have will be a range of probability. If that falls in that category, that particular MEC host will be selected. So we have used the transmission latency, system utilization, and with application consent and latency consent. For example, a UE will have a certain app characteristics that it needs to be served within certain amount of time with the resources requirements such as RAM and CPU requirement, and the secondary storage requirement. So MECO will collect the periodic info from the MECH, and it will see that where it is the best to send the application, to run the application from the perspective of the system, that is the complete system. So this methodology will, the host selection algorithm has certain aspects like context is creation as mapped to a task arrivals. Then it will have the application parameters of a particular app. Then MECO will check the MECH resources available, and then it will optimal host, it will allocate the optimal host based on the probability. And we have used an reinforcement learning algorithm to update it. And then there is a context deletion. So this signifies that the task is completed, and now that particular task is no longer will be running, and resources corresponding to it will be released. So as this, we have already seen that this flow was earlier, like in the UE request for the app list, then in the same flow, the MECO will pull the resources from the MEC host, and once that app characteristics and app parameters are received and a host is selected, it informs the selected MECS to run the app. And when context deletion is done, then it will inform MEC host to end that application and release the corresponding resources. So this is our algorithm where we have applied the reinforcement learning to optimize the cost. So we have developed the cost function such as it includes the transmission cost and the computation cost involved at each MEC host, and corresponding to it, a reward is calculated, and that instantaneous rewards after some time will calculate in an interval, and then will calculate the change in reward. So the change in reward will decide that whether we are going in the right direction, that our system is stable and it is giving the optimal selection and optimal probability. In case it is not giving, we'll change this direction and will update the system accordingly. So this is the reinforcement learning based algorithm. So we have seen, so we'll have that resources or use that MEC host and app parameters, and we'll get the optimal probability. So the initial will have the equal probability assigned to all hosts, which will be updated based on the rewards received. So we'll calculate the instantaneous rewards as shown in the previous slide, and then we'll update the probability vector like with the value of the reward, and we'll normalize the probability so that it does not exceed, and it will be in the range, and the summation of it should be 1. So our algorithm will be the optimal when we have the reward tending to 0, means this Pik plus 1 will Pij k plus 1 should be equal to Pij, such that this is 0, this is 0. So we will have reached the optimal probability. So MEC host parameter. So we have used the host configuration, that is resources available at the MEC host. So we have tried with the various level of configuration, which gives the optimal performance. Then another thing which depends is the arrival rate of application. So this is very much important from the perspective of the service provider, because they want to know that how they will be getting the traffic and characteristics of the network, so that they can plan the resources optimally. And the other part is app characteristics. So it decides the resource requirement. So this is also very critical in deciding the offloading tasks at the MEC host and planning the MEC system, because MEC host requires a lot of computation and resources which are costly. And on the similar way, they can also decide on the physical location on the MEC host. This is important because we have talked about the transmission time. So that is the time from UPF to MEC host. So if we want to do some offloading task and we have to send some data for processing, so it should serve a particular latency. So we have to see that how much latency we can allow. So for one particular configuration, I'm showing, like say we have the 3 MEC hosts with certain configuration like RAM 24 GB, 48 GB, and 64 GB, and the secondary storage as 512, 1024, and 2048. The probability varies, like we can see that the hosts which are having the more number of resources is getting the higher probability, so that the overall cost of the system is reduced, and there is a optimal allocation. So I think this is from my side for the MC host selection. And if there are any questions, we like to have any questions if there are any.
Okay, thank you, Professor Arzad Alam Hirani, Mr. Vinod, Mr. Ashish, and Mr. Gaurav. This was very beautiful, informative, and excellent presentation. All the basics and concepts were well covered in this presentation, and introduction to MEC, ETSI architecture of MEC, implementation details of MEC in the test bed, and a live example of application development was all well covered and very excellent. I don't see any specific questions regarding this presentation. So I just, as a reminder, I am, please be sure to type your questions into the question box in your control panel. So regarding this presentation, it seems that there is no question regarding this presentation. We have some questions like Khaja Mohiddin Sheikh. He is asking, dear sir, is this session recording will be shared with participants? I will, Mr. Asif will, let you know about this. This session is being recorded, but will it be shared with the participants? It is not yet decided. So another question, it was from Pamela Kumar. Actually, it was for Professor Arzad. He is not present. So Pamela was asking, do you have any users of the test bed?
So I
So,
can answer that.
okay. Sir, you can answer that.
On behalf of Professor Azad, because and right now what we have done, we have shown you the application that we have built within ourselves. So, however, we are running a 5G hackathon, MEC 5G hackathon, to cater the application that are developed by the other users, and we can cater it in the MEC platform, this MEC ecosystem. So there already one haptic application, and people have registered from other sources also. So we'll definitely cater those applications. So that's the whole purpose of this running this MEC 5G hackathon, to bring different level of users to run their applications over this. So right now we don't have it, but in the near future we'll definitely have.
Okay, sir. One more question is there. What are the basic challenges for connectivity from server to client or vice versa, like MECO server to client app? Have you got the question, sir?
Now, where is that question?
What are the basic challenges for connectivity from server to client or vice versa, like MECO server to client app?
Where it is written, I think, I mean, in
Uh,
what,
it is in the
in what context it
chat
was
box.
asked?
It is
Could
in the
see it in
chat
the,
box.
huh?
It is in the chat box.
Okay, chat box. So basically, MECO server, see, there are three parts of the application. I just trying to understand the question. The three part of the application, one is client, one is edge, and one is the cloud. So what was happening before MEC was that everything was being sent to the cloud. So there was some latency. So there was some, I mean, the cloud server has to manage each and everything. So if we bring in the MEC MEC edge server, then the computing part of computing will be covered at the edge server, whereas the uh, whenever it is as and when event triggering has happened, some data needs to be sent to the cloud. Can be sent from the MEC edge to the cloud, as well as from the client to the cloud itself. So there is a two-way connection. Client can send directly to the cloud engineer, and whenever it needs, it can send it to the S server. So that's why the whole idea of when I showed the ping to the client as well as ping to the cloud server as well as to the S server. The idea was that there's a three-way communication established between client, edge, and cloud server. So challenges, I mean, the challenges, if you are referring to, are basic for connecting so server to client or vice versa, like MECU.
Okay,
So
thank you, sir.
MECU is not the server actually. MECU is a facilitator, so it keeps context of all the application that are running in the MEC host. So that will be actually, instead of MECU, it will be the MEC host, or we
Okay,
can
thank
say
you, sir.
at server.
Thank you, sir. Thank you, sir, for your
So,
these valuable answers. So now we will take a break for 15 minutes. We'll be back sharp at 12:15, and we will have second expert talk on massive MIMO algorithms by Professor Saif K. Mohammed. So we will take a break of 15 minutes now.
okay, thank you all. Thank you all for being there, and thank you.
Thank you, sir.
Thank you.
Mudassir, can you present the? Can you flash the agenda that it's showing the break? That would be great for listener.
So Asif, can you please take over? Still, I am the presenter, or please pass on to the next presenter.
Yeah, can you flash now? I make you presenter now.
Sorry.
Can you flash the agenda that shows the break?
Okay. Mr. Asif.
Yeah, now it's showing, but not the agenda.
No, you want to see an agenda for next session?
Yeah, if you can flash, because that's showing the break on the agenda itself.
Agenda, I don't have with me. Wait for me.
Okay, let me check if in my mail.
Okay. If you have an agenda with you, you can show it up.
Yes, Asif, this is Professor Saif.
Yes, Professor.
Yeah, so how do I enable my webcam?
Can you click on the it's near mic button, the webcam on, or let me just request you just a second.
Just trying something.
Yeah, it's visible. Useful.
All right. Oh yes, I can see it now. Yes. Okay. Good. Yeah. So I'll mostly talk, and the slides are with Venkatesh, so he'll be making most of the presentation. I'll take about 10 minutes or something like that to just introduce the topic. Okay.
Yeah, sure, sir. The session is still live, sir.
Okay.
So I'll make Mr. Venkatesh as a presenter. Your
Yes, you can.
presentation also he will present, right?
Yeah, he will be presenting, but I just need 5-10 minutes to introduce the topic.
Yeah, that's fine. That's fine. Yeah. Hi, Mudassir. The time is 12:14. So now I think you can take over.
Okay. Okay, Mr. As. Mr. Asif, am I audible?
Yes, you are audible.
Okay. So let us now begin our second session of this webinar. And our second expert talk will be on massive MIMO, multiple input, multiple output algorithms. It will be presented by Professor Saif K. Mohammed. Let me give a brief sketch of Professor Saif, sir. Professor Saif is currently an associate professor with the Department of Electrical Engineering, IIT Delhi. He received the BTech degree in Computer Science and Engineering from IIT Delhi in 1998 and PhD degree from the Electrical and Communication Engineering Department, IISc Bangalore in 2010. From 2000 to 2003, he was with Shawnee Networks, Santa Clara, USA, as a senior chip architecture engineer. He was a systems and algorithm designer with the Wireless Systems Group, Texas Instruments, Bangalore, India from 2003 to 2007. From 2010 to 2011, he was a postdoctoral researcher at the Communications System Design, Electrical Engineering Department, Linköping University, Sweden. His main research interests include wireless communications using large antenna arrays, coding and signal processing for wireless communication systems, information theory, and statistical signal processing. He holds 4 granted US patents in multi-user detection and pre-coding for MIMO systems. So you can switch now to Professor Saif, sir. Welcome, Professor Saif, sir.
So you can unmute yourself.
So thank you, Mudassir. Thanks a lot for the introduction. It's a privilege for me to talk to all of you about whatever work we have done, especially my group has done in this 5G testbed project. So essentially, I am an expert in physical layer, design of algorithms for MIMO systems. And at IIT Delhi, we have set up one of India's first massive MIMO base station, which is there in our lab. Massive MIMO, as you already know, is one of the leading technologies in 5G. So in this project, because we have a lot of partners, a lot of IITs have been working together, and being at the physical layer, any the algorithm that has to be implemented at the physical layer has to work, very nicely, in tandem with the hardware. And since the hardware was designed, especially the base station was being designed at IIT Madras, so students from my team were at IIT Madras for quite some time. I myself made several visits. So together with the IIT Madras team, we implemented some of the very important modules, which are essentially the channel estimation module, the channel equalizer module, because without channel estimation we cannot do channel equalization. And so these two were the important blocks that we did. And then apart from these two, we were also involved with CVIT, because CVIT is another organization which is there, in IIT Madras Research Park, and they are actually involved in the hardware design also. So another very important part of any communication system is control signaling. And control signaling basically means whenever we do any kind of communication, whenever we send packet, a transmitter sends a packet to a receiver, and then the receiver decodes it and then sends an acknowledgement back. So this acknowledgement is some kind of a control information which tells the transmitter that okay, the packet has been received correctly. Or if the packet has not been correctly received, then it sends the receiver sends a negative acknowledgement, and then the transmitter will actually retransmit the packet. There are several types of control informations, in 5G NR, but the way that they are actually transmitted is quite, it's not so easy to understand, because at the end of the day, control information is an overhead, because we are not transmitting any new information. Control is basically to make sure that whatever communication is happening in a reliable manner. So so there is always this constraint that the control overhead should be as small as possible, and so the control signal has to be kind of fit in, it has to be designed and fit in into the the frame structure of 5G NR. So one problem is the decoding of this control information, because there is no set rule that the control information will always arrive on this particular resource block. So at the receiver, then the only option is that we have to do some form of blind decoding. Blind decoding basically means that we have to sort of scan the we know the entire space, or we know the part of the resource block where it is supposed to be, but we don't know exactly where it is, and therefore some kind of search has to be done, and then we call it as blind decoding. Blind because we don't know exactly, and also so that is a challenge actually. And so we did some interesting work, and that work is also going on right now on the blind decoding of we call it it's called the physical downlink control channels, PDCCH. So that work is again with CVIT. So we thought in the given time that we have, we will maybe discuss a little bit of channel estimation equalization, and then also what we have been doing on the blind decoding of PDCCH. So please feel free to ask any questions. So I think I'll now request the PhD scholar, Mr. Venkatesh Kamameti, who worked extensively on these algorithms, and he's also working currently on, right now on the blind decoding algorithm. So he will be presenting, at least in the given time, whatever we have. He tries best to present whatever we have done so far in this project. Thank you.
Mr. Venkatesh, if you can switch on your camera.
Sorry, ma'am. Actually, cam is not working fine.
Okay, no problem.
Yeah. Thank you, sir, Sai sir, for the brief introduction. And now I am going to start the presentation on this channel estimation, equalization, and blind decoding of control signaling in 5G NR. So these are the contents of the presentation. So first I will give a brief introduction to the history of communication. Later we will look into the basic communication systems. Then what is wireless channel and estimation and equalization. Then I will give small introduction to MIMO communication system. Then we will see the mathematical modeling of this channel estimation and equalization. So then I will discuss the work done on channel estimation and equalization in 5G testbed project. So we designed this in Vivado and Vivado HLS implementation. So I will give a small introduction to what is Vivado and what is Vivado HLS. So then I will give small step, the general steps. So how we are going to dump this code from Vivado to this FPGA board. Later, we'll be looking into this 5G frame structure and what is bandwidth part and its importance, and this control resource set. Then it is 5G under PDCH configuration, and we are designing this search space and how we are going to design it, and what is the importance of search space, and blind decoding of this PDCH, and work in progress in this 5G test bench project. So the first set of contents are for this channel estimation and equalization, and the second set of contents are for this blind decoding algorithm. So if we look into the history of wireless communication, so it first started with this James Clerk Maxwell, and he reduced all the current knowledge into a linked set of these differential equations with 20 equations in 20 variables. So his work was published in this on physical lines of force in 1861. And later in 1873, he gave the well-known Maxwell equations. These are the 4 Maxwell equations. And later in 1886, this Fetch discovered the electromagnetic waves. And studying the Maxwell's equations, he predicted that Maxwell equations are right. He proved it experimentally. So later so this is the experimental setup used by Hedge. So where this is the first radio transmitter, where a capacitor loaded dipole resonator consists of a pair of 1 meter copper wires with a 7.5 mm spark gap between them. So then actually the Jagdish Chandra Bose, mostly when we talk about wireless communication, we say that Marconi discovered this, developed the radio waves and all the things. But first it was started by an Indian, and that too he is Jagdish Chandra Bose. He performed pioneer research on radio waves and created these millimeter waves as short as that 5 mm. Bose's work actually predates that of Marconi, who is most often associated with the development of radio. But Marconi commercialized his work with radio waves, whereas Bose was purely interested in radio waves as a scientific endeavor. So later, Marconi duplicated this Hedge short-range experiments and then succeeded in sending signals over long distance. By 1899, Marconi was constructing this wireless station on both sides of the English Channel, and in 1901 he installed transmitter and powerful enough to send messages across the Atlantic. So and this is his first trans-receiver experiment. And these are all remaining things. All these years and whatever they have done in these years. So all it started with this generation of mobile communication. With the advancement in the electronics, Martin Cooper, an engineer at Motorola during 1970, worked on a handheld device capable of two-way communication, invented the first generation mobile systems. So it was initially developed to use in a car. The first prototype was tested in 1974. The first generation of mobile communication was deployed in Japan by Nippon Telecom and Telegraph Company in Tokyo during 1974. Then this first generation of communication came into picture in 1981, second generation in 1991, and you can see all those years and whatever the generations that are at present. So the first generation of mobile communication, this is like first time calling was introduced in these mobile systems, and So whatever the talk I am talking, mostly it is related to this physical layer perspective of view, and I am not talking anything about transport layer or network layer. So here in physical layer, we used this analog FM modulation in first generation, and it used this FDD scheme and typically allocating bandwidth of 25 megahertz, and it is a advanced mobile phone systems. And the multiple axis is the frequency division multiple axis. This generation of communication coverages very small areas, and there is no roaming support, and the sound quality was low, and even the speed, the data speed is about 24 kbps. And the second generation of mobile communication, we shifted from this analog to the digital, and it supports voice and SMS both. And then it is a moderate mobile data service, and the example of this second generation is this global system for mobile communication, GSM. And here we use both time division multiple axis and frequency division multiple axis, and the speed is around 24 kbps. So we all know about this 2G, but there is some 2.5G and 2.75G, where in 2.5G we introduced the concept of this GPRS, and 2.75G is we introduced the concept of this edge, so which provides a faster service than the 2.5G. In third generation, it's like a internet system was improved, and we are having this better system, and the better and the data capability is more. So here we are using this code division multiple axis, offers this high speed wireless network, and the speed is around 2 Mbps. So these 3.5G and 3.75G, we introduced these new systems called high speed downlink packet access and high speed uplink packet access system. The fourth generation, we know the current generation we are running is this fourth generation, and it is like a IP-based protocol, and we are here having this LTE and Vivo LTE. And here first time we introduced this OFDM, this orthogonal frequency division multiple axis, and it supports like a high data speeds of around 100 Mbps. So 5G is like it's not only spread in like among the users, they introduced other things like massive IoT and critical IoT. So in massive IoT and critical IoT, most all the industries will be using these massive IoT and critical IoTs. Even household devices are also using this Internet of Things, and it's like mobile broadband based communication. So whatever the like generation of communication is, this is the basic communication system. Whichever the generation, whether it is the 1G, 2G, 3G, or 4G, whatever it is. So the basic communication system will be having a source, a transmitter, a channel, receiver, and a sink. So the source is nothing but a transmitting user, and the transmitter is not a single block. It comprises of this source encoder, so which encodes the source bits. So you can see this. So this transmitter is having this source encoder, which encodes the source bits, and this channel encoder, modulator, the pulse shaping, and digital to analog converter. And there is this baseband to RF, so which converts these low frequency signals into the high frequency signals, and then transmit. This transmit is nothing but antenna system. So in case of wireless communication, it is an antenna. Otherwise, in case of like wide communication, it can be a coaxial cable or something. So coming to receiver part, receiver is into the exact reverse procedure done at the transmitter to get or recover the original transmitted signals. So as mostly we will be concentrating on the channel, and here our channel is mostly this wireless channel. So it's nothing but this wireless channel or this wireless environment. So what is basically this wireless channel? So if ever like this for example, you are having a transmitter and a receiver. Transmitter and receiver both are like antennas, and if ever you are having a line of sight component. Line of sight means it is a direct link between the transmitter and receiver wirelessly. So if ever you are having only one path between the transmitter and receiver, and that to a direct path, we term it as this line of sight path. And even at a receiver, determining or decoding the transmitted signal is easy only if you are having only one path on the two line of path. But in wireless communication, you will have reflectors, basically buildings, and refractors. So those are the glass and other objects. So that reflects the signals, and this reflected signal is all received at the receiver. You can see here we are having many reflectors, and all these reflectors are reflecting the signal, and all are received at the receiver. So from the figure, you can see that you have a line of sight component with 4 reflectors and are received at the receiver. As a result, the transmitted signal will be received at the receiver in multiple paths. If ever these signals, so these are all the reflectors. So all the signals will be reflected in all the directions, and these are multiple paths. If ever these signals add up at the receiver destructively, then the signal power degrades, and this results in fading. It is clear that from the figure, it is clear that the signal received at the receiver will have different delays, because all the paths followed by different reflectors is different. Definitely, they will be adding up at the receiver at different instances. So due to this, we will be having a delay spread at the delay spreading of the transmitted signal at the receiver. So if ever at the receiver, if the reflectors are moving or the receiver is moving, then you will be having this Doppler spread. So all these affects the received signal and degrades its power. So knowing the type of channel, estimating the channel, and equalizing the effects of the channel helps in better decoding the transmitted signal at the receiver. So this is a mathematical modeling of the received signal. It's nothing but a convolution of the channel impulse response with the transmitted signal. Here R of t is the received time domain signal. H of t comma tau is the channel impulse response. S of t is the transmitted signal, and N of t is the noise at the receiver. And coming to MIMO communication systems, MIMO is a multiple input, multiple output system in which we have multiple antennas to transmit and multiple antennas to receive. So MIMO system helps in increasing the data rate by using the spatial dimension, and it helps in better understanding of the communication channel. So this is here I have taken an example of 3 transmit antennas and 3 receive antennas. Where this is the channel between these antennas, where the component H11 is the channel gain between the receiver 1 and transmitter 1, and the channel gain H21 is the channel gain between receiver 2 and the transmitter 1, and similarly all the others. So estimating MIMO channel helps in a better understanding of the channel, and this indeed helps in increasing the data rate. So mathematical modeling of this channel estimation. So these whatever the equations are given here, those are mainly for this CISO type of channel, where single input and single output channel. So the received DMRS is nothing but the demodulation reference signals. So we transmit these demodulation reference signals along with the transmitted data, so as to know the wireless environment between the transmitter and the receiver. So this DMRS vector is known both to the transmitter as well as to the receiver. So during the connection establishment between the base station and the UE, that user equipment, the base station will send these RRC parameters. In these RRC parameters, it will send one ID called NID, and this based on this NID, the receiver can know whatever the DMRS vector that is transmitted by the base station. So here the received DMRS vector is a vector of length 6, and H is the scalar component and is the channel gain, and D is the transmitted DMRS vector of length 6, and N is the noise vector of length 6. So you might be having a question is why we are taking the length of 6. So these are the channel estimators. So we are taking the length of 6 because means I will be introducing this PRB, physical resource block, in the coming slides, like in the explained in 5G frame structure. So physical resource block what is that? This physical resource block, if ever you are sending a physical resource block over a wireless channel, so it is assumed that this physical resource block is received at the receiver in a coherence in a coherent time interval. Coherence time interval is the interval in which the channel is constant over the this interval. So that's why that's why this, whatever the physical resource block is there. So this is having these 12 resource elements, out of which 6 the green are the data elements and the blue one are the DMRS elements. So we will be extracting these DMRS data. So that is nothing but the received data Y is equal to HD plus N. So where D is the transmitted DMRS vector. So we are estimating the channel to the channel estimate H cap, that is approximately to the D admission Y by 6. So we'll be getting a channel estimate from the first equation, and then the second equation, later equation, we will be having a noise estimate also. So once we got these channel estimates, so now we are going to equalize the data. So here you can see that as I said, that green ones are the data. So we estimated this channel by using that DMRS, and we use the same channel to the to equalize the data symbols. So as I said, the channel will be constant over this physical resource block. So we will be using the same channel, same estimates from the DMRS. So this is the received data vector. So in which is Y is the received data vector and H is the same channel gain. So now we have to equalize this channel effect by from the channel estimate that we have estimated. So the estimated transmitted vector is X cap is approximately equal to H cap emission by this norm square of H cap. So these are these design, whatever this channel estimation equalization we have done, this is for like, this is a basic design, and we have designed only for these scissor systems. So where is channel estimator and equalizer performed? As I explained you before, the basic communication system, there I didn't mention anywhere the where the channel estimator or equalizer is. So here you can see the where the channel estimator and equalizer is performed. So once you are converting this analog to digital converters, and after filtering it, there the filtered data will be mostly it will be that elements in the physical resource block. So that the elements in the physical resource block will be going to the channel estimator as well as to the channel equalizer. The channel estimator just extracts the DMRS symbols from the physical resource block and gives the estimate to the channel equalizer. The channel equalizer, it extracts the data vector from the physical resource block, and it perform the equalization and send the estimated transmitted symbols to the demodulator, and then the remaining process like channel decoding and source decoding is performed. So whatever the design this channel estimator and equalizer, we designed all these estimator and equalizer in C and C++, and then the thing is we have to run these C codes or C++ codes of this channel estimator and equalizer over an FPGA. So we used this Xilinx design suite to program FPGAs. It is nothing but Vivado design suite. So these design terms, it supplies the design terms with the tools and methodologies needed to leverage this C-based design and this optimizer reuse. So we can do this either C-based or C++-based design of this channel estimator and equalizer in this Vivado and Vivado HLS. So it will create this IP subsystem where we can integrate and automate and accelerate the design. So I will give a screenshots of what is this Vivado and Vivado HLS. So Vivado HLS is where we do this C and C++ coding, and we will create these intellectual properties, that IPs in this Vivado HLS, and we use these IPs in the Vivado. So this is that Vivado HLS, like a screenshot of Vivado HLS, where you can see that there is some basic C code. So you'll be having this, you'll be creating a project, and in the project, whatever the project, like here we created this channel estimate and equalizer project, and under that project we developed the C and C++ code of how we are going to estimate channel, we are going to estimate the channel and how we are going to equalize it. The other thing is Vivado. Once you created this C and C++ code, so then once we do this successful run, then we are creating the IPs from the C and C++ code. These IPs will be used in the Vivado. So Vivado, here is the like screenshot of Vivado. So here Vivado, whatever the blocks here are having, these are the IPs that are created using this Vivado HLS, and we will be connecting all these IPs, and we will be generating a block diagram as seen in this basic block diagram. So we can generate all the source decoder, source encoder, and everything, and we can create a successful block diagram. And here I will be showing the IPs created by us. So these are the channel estimation IPs. Here the first estimator will give only the channel estimate, and here we just neglected the noise. So we from the spreadsheet of this Xilinx board, we came to know that the noise in this Xilinx board is very less. So what we did for a basic thing, we just remove this noise estimator, and we just designed this channel estimator block. And later we created one more estimator with both this channel as well as the noise estimator. So the thing is, if we are having only this channel estimate, the equalization will be very easy. But if you are having this channel estimate and sigma estimate, the equalization will be difficult. But the thing is that you will be getting less bitter. So this is the channel equalizer block. So here you are having two block diagrams. In the first block, we just normalized the channel. In the second block, in the second block, we normalized the channel effect, and first block is a equalization. So this is the complete block diagram. So from the basic block diagram, as I mentioned that from the basic block diagram, we can also design the same block diagram in the Vivado, and this is the overall block diagram from the receiver. So from the time you are receiving the signal till the time that you are decoding the signal. So in this block diagram, our channel estimation and equalization is present at this particular place, and I will give a screenshot of exactly where the channel estimator and equalizer is. Here you can see that we are having that channel estimation. Then we are having this channel interpolator. So all these blocks are to just combine the data. So these all these blocks are just to as I said, we are having this physical resource block. So we will be combining data from all the physical resource block and making it as a one vector, and we will be equalizing the vector by vector. We are having here 16 channels, and in each channel we are having each channel estimate and equalizing the effect of each channel in this data vector. Having 16 channels, so that's why you are having 16 data input vectors, and you are equalizing all the channel effects in this equalizer fe underscore 0, then we are normalizing the channel effect in equalizer underscore dap underscore 0. So this is so here I will be giving the basic steps how we are going to whatever the code designed here, how we are going to dump this code over the FPGA. So from Vivado to this FPGA board. So first, once we had the successful run of the block diagram over the Vivado, we will be generating these bit streams in the Vivado. So once the bit stream is generated, we will export this bit stream onto a corresponding hardware or the whatever the hardware that is connected to your system. So once this is done, then we will launch that software development kit. So in the software development kit, we will be creating a project in this SDK, and then we will be programming. So in the SDK, once you created the project, then you there again you have to select on which hardware you want to export this generated bitstream or export your code. So there, once you selected that hardware, there again you will be programming that FPGA board with these generated bitstreams. So once you program this FPGA board with these generated bitstreams, then you will try to run the project. If it had a successful run, then definitely the whatever the say receiver block is there, that will be running successfully on the FPGA. If ever there are any errors, then you have to rectify it from the beginning, like from Vivado HLS you have to rectify the C code. Then once the C code is rectified, then you have to again generate these IPs. Once the IP is generated, again you have to place that particular IP onto this Vivado. Then again you have to create this bitstream and all that things. So until this point, it is all about this channel estimator and the equalizer. Whatever the channel estimator equalizer we have designed in this Vivado and Vivado HLS. And the next topic will be mostly on the blind decoding. As Professor Saif Khan Mohammed has already introduced what exactly blind decoding is, and how we are, and I will be explaining how we performed that blind decoding. So here this is a screenshot. As I said, we will be generating the bit streams and all the things. You can see on the left panel all the things, means how we are going to like running the simulation and the RTL analysis, synthesis. All these are like from then you will be doing this generated bit stream and all the things. So frame structure in 5G. So this in 5G the frame is of 10 milliseconds length, and this frame is divided into 10 subframes, and each subframe is of length like 1 millisecond. And the number of subframes, the number of slots, again this subframe will be divided into slots, and the number of slots in the subframe depends upon the type of numerology we are using. Here you can see that of these 10 subframes, the first half of the subframe is named as half frame 0, and the second half is named as half frame 1. So why again this frame is divided into halves? So it is basically that you will be having two links. One is the uplink communication and the downlink communication. So uplink communication is nothing but from the UA, from the user equipment to the base station is the uplink communication, and from base station to the UE is the downlink communication. So of a frame of length 10 milliseconds, 5 milliseconds will be used for this uplink, and the other 5 milliseconds will be used for the downlink communication. So as I said earlier, that the number of slots in a subframe depends upon the type of numerology, and the numerology is nothing but mu, that is the subcarrier spacing. So you can see that for the subcarrier spacing 0, the number of slots per subframe in the fourth column, you can see that only one slot is there. But if the subframe is 1, then you are having 2 slots. For the subframe of for the subcarrier spacing of 2, you are having a slots of 4. So it's on there. So, and one more thing is that each slot will be having like 14 OFDM symbols. So as the number of slots increases, the number of OFDM symbols in each subframe also increases. So here you can see the subcarrier spacing also, like it is like for subcarrier spacing subcarrier spacing configuration 0, the subcarrier spacing is 15 kilohertz. For subcarrier spacing configuration 1, the spacing is like 30 kilohertz and all the things. So resource grid. So see, what is this resource grid? So I will explain. Actually, I have generated one example where I will be explaining whatever all the things means. What is this resource grid and what is the resource block? Everything in the later example, I will give a like detailed explanation of it. At present, here we will be looking into that say that notations. So here you are having for a given this numerology and a carrier, a resource grid of like n grid size comma mu and n subcarrier spacing and resource block are there, and out of which that n symbols for subframe are there. These are all the numbers. So you can see this whatever the like details are here. So those numbers are mostly given in the table. This is how this resource grid looks like, where this each this rectangular box is nothing but a resource element, and you can see the dimensions of this resource grid. Actually, it is taken for a subcarrier spacing configuration 0. That is means only one slot will be there in one subframe. So here you can see that. Bandwidth part. So actually in 4G, the thing is whatever the available bandwidth is there, you will be using all the available bandwidth in 4G. Due to that, you will be like it is very difficult to do the multiple access, because whatever the bandwidth is there, the bandwidth is being used by either one user or is like so. So that's why in 5G they introduced a new concept called this bandwidth part. So where you will be having this flexible bandwidth per each UE, and actually in this 5G, so bandwidth part, so you will be having like 4 bandwidth parts given for each UE, and in both in uplink and as well as in downlink, you will be having like 4 bandwidth part. And UE can be, as I said, it can be configured with up to like 4 bandwidth parts, and every time only one bandwidth part will be a active bandwidth part. So downlink control information. So what exactly this downlink control information consists? It consists of this uplink resource allocation. So during this connection establishment process, so it will for example, UE you want some like multimedia data or some other things. So if ever you want some multimedia data, this downlink control information will give exactly the resource elements where this multimedia data say asked by the UE is present in the resource grid. It will give so then it will give the description about this downlink control information consists of this description about the downlink data transmitted to the UE, and it also have the power control elements. So this is a typical like downlink scenarios in which the base station was trying to communicate with like nearly 7 user equipments within the region. So you can see that so one like UE1 wants some like multimedia data, UE2 want to just make a video call, or UE2 wants some other requirements. So the what happened is this base station will be sending this downlink control information to each UE. So in the downlink control information, the downlink control information is later processed and named it as like PDCs, the physical downlink control channel, which consists of what exactly the UE request means, where exactly the UE resources are there. So this is a block diagram in which we are converting this DCI to this physical downlink control channel. So once we have this DCI, we will be attaching this CRC check to the DCI. Then we are doing this RNTI masking, then interleaving. So these actually controls in control channel, will be using this polar coding. So here using the polar coding, and this control channel information is mostly QPSK moderated. And you can see this is a basic block diagram. And I will be explaining about what is CCA, what is CCE, REG mapping, and everything in the later slides. So this is coming to 5G NR PDSH configuration. So in this 5G NR PDSH configuration, you will be having a core set configuration. Core set is nothing but control resource set. So I will, in the later slides, I will explain more about this control resource set. And then in the 5G PDSH configuration, you will be allocating these PDSH resources to core set. So how we are doing means allocating PDCH resources to core set. So it is mostly based on like actually we will be dividing this core set into CCS. So CCS are nothing but control channel elements. In the later slides, I will explain all about these control channel elements and everything. Then once that is done, we will be defining this physical downlink control channel search space. What is this search space and what is this physical downlink control channel search space? So coming to control resource set, so control resource set is nothing but a block of elements. It consists of these physical resource blocks or REGs. So each REG will be having these 12 resource elements, and courses are configured in units of these 6 PRBs. It is configured in units of 6 PRBs because the length of one control channel element CC is equal to like 6 PRBs, and the core set, the maximum size of core set in the time domain will be like 3 OFDM symbols. And where a UE can be configured like with up to 3 core sets on a bandwidth part. As I said that each UE can be configured with up to 4 bandwidth parts. So UE can be configured with up to like 12 core sets. So how we are going to map these PDCH data onto the core set? So we are mapping these, we are dividing this PDCH data into control channel elements. So, and we will be mapping the, as I said earlier, one control channel element is equal to like 6 REGs, and one REG is equal to 12 REs, resource element. Out of these 12 REs, 9 resource elements will be used to send this PDCH data, and the remaining 3 are used to send the DMRS. So again, as in this channel estimator and equalizer, here also we will be having this DMRS. And so for each DCI, this download controller information, you will be having 2 power n CCs. So where like n is equal to 0, 1, 2, 3, and 4. So the number of CCA of the DCI is determined by the aggregation level. So aggregation, basically we are having like 5 aggregation levels based upon the like length of these based on the length of the PDCH. Once like you are having this download control information, and this download control information will be transformed into the PDCH. So depending upon the length of this PDCH, so the base station will decide which aggregation level to use it, and based upon the aggregation level, the number of CCs are fixed. So on the like, so using this number of CCs, the base station will send this PDCH data to the corresponding UE, and we'll be having a CCA to REG mapping. So this CCA to REG mapping is like it can be interleaved or non-interleaved. So I will be discussing about this CCA to REG mapping in the later example. So that whatever the set of PDCH candidates for a UE are there, they can be monitored. They can be monitored by the UE, and so where to monitor and how to monitor these PDCH data is given by this PDCH search space sets. So you will be per bandwidth part you will be having these 10 search space sets, and these search space sets are like two types. One is this common search space set where the search space set is common to all the UEs, and the other is like UE search space set which is specific to a UE. So designing search space. So before designing search space, first the UE determines the start of the bandwidth and the size of the bandwidth from the RRC parameters. So once you got the start of the bandwidth and the size of the bandwidth part, then it will look for the position of the starting position of the core set. Once we have the starting position of the core set, the UE monitors the particular slot to see whether there are any PDCH present in the particular slot or not. So it implements this particular equation, and if ever the equation, whatever that equation, if ever the result of the equation is 0, then it assumes that there is a PDCH associated with the slot. So these are the different search space configurations. So depending upon the search space type and the aggregation level, you are having the maximum number of PDCH candidates. So, and here there is a calculation of size based on the aggregation level. So hash function, what is this hash function exactly is? So the thing is, once you are having the core set, now you should know where to place the PDCH data in the particular core set. So for that, you will be getting you require the CCE indices. So for a particular core set, for a given core set, for a given search space set, and for a given slot, so the CCE indexes are determined by using the following equation. So this equation will give, based on the aggregation level and the maximum number of PDCS candidates and the slot number and number of CCEs in a particular core set, it will give the exact locations of the CCE indices. So then once we got the CCE indices, now we are going to map this PDCH data over these CCEs. So further you are having the you can perform this CCE to RAG mapping. So how we are going to perform this CCE to RAG mapping out deep mapping. So you will be having for example for a search space for a CCE or J, the REG bundle is as follows. So these whatever the equations I am presenting here, all these equations are from the standard 3GPP standard 38.211 and 38.213. So now the thing is, so once like for example in a typical communication scenario, the UE wants some multimedia data from the base station, and now the base station will send the control information to the UE. Now the UE has to decode the download control information from the corresponding PDCCH. So in the convention method, what we do is, so we do the exact reverse process, means we will be getting the PDCH payload. So prior to getting this PDCH payload, you will be searching in all the aggregation levels. So first you will start with a lower aggregation level, and then you will decode the PDCH payload from the aggregation level. Then you decode it, and then you do the exact reverse process, and you will check for the CRC check. If ever the CRC check doesn't matches, then again you have to go for the next aggregation level, and again you have to determine the CC indices and PDCH payload, and again you have to do the reverse process. So every time it is you will be going to the CRC. Every time you will be doing the CRC check to do the to decode the PDCH for the corresponding UE. So it is consuming a lot of time, and and even you can see that the number of blind decodings. So the number of blind decoding instances for a given slot and for a given say subcarrier spacing is limited. So you have to decode the data within these limited searches. So if ever you are unable to decode the data within this say maximum number of searches, then the download control information is lost, and the base station has to again send the data. So it is like a overhead to the base station, and even it takes it consumes a lot of time. So what we proposed is that we proposed a new method like DMRS correlation method. So actually, as I said earlier, these CCs will be having these REGs, and in each REG will be having like 12 resource elements. Out of 12 resource elements, 9 resource elements will be used for PDCH, and 3 are used for this DMRS. So the thing is that DMRS for a particular UE is always the same. So depending upon the NID, the NID is the ID given by the base station to the UE. So based upon that NID, you can determine this DMRS. So the receiver will come to know about the transmitted DMRS. So once it extracted the DMRS, we perform a correlation between the received DMRS and the transmitted DMRS, and we will compare this correlation with a predefined threshold. So predefined threshold, and if whatever the correlation we perform, if ever it is greater than the threshold, then we assume that the particular DCI is for the given UE. And whatever the search we are doing, this search, this blind decoding search, everything is only that UE specific search space. So as I said earlier, I will be explaining everything in a example, and here is an example. So for example, this is like a frame of 10 milliseconds, and as I said, this frame is divided into like subframes, and each subframe is of 1 millisecond. And the horizontal axis is the time axis, and vertical axis is the frequency resource axis. So here you can see that bandwidth part. So now the bandwidth, for example, we are selecting for a UE1, we are allocated the bandwidth part 1 in like subframe 1, and bandwidth part 2 in the subframe 2 and 3. So the exact spread of the bandwidth in a time domain is not given in the standard, but in the frequency domain, you'll be it is having some limits. So all the limits are given by these RRC parameter. So once once we get the bandwidth, so once we are having the bandwidth part, so now I will take the example of bandwidth part, and whatever the things are, and I explain whatever the things are there within the bandwidth part. So this is a bandwidth part. So in this bandwidth part will be having these resource elements. So you can see this each square grid is nothing but a resource block. So the size of the resource block is 1 subcarrier per 1 OFDM symbol. So the combination of 12 consecutive subcarriers. Sorry, the combination of 12 consecutive resource elements is nothing but one physical resource block. So it will be having like 12 subcarriers per 1 OFDM symbol. So in this particular bandwidth part, you will be this core set will be occupying some position of the bandwidth part. Here I like use the maximum dimension like 3 OFDM symbols, but it is not that the core set has to be present in the starting of the bandwidth part itself. It can present at anywhere within the bandwidth part. So whatever the position of the core set is there, the position of the core set will be given by us during this RRC connection establishment process. So now we'll be looking into the core set. What is the core set, and what will be there within the core set? So here is a typical example of a core set of like 54 physical resource, means each element here is one resource, physical resource block. As I said earlier, physical resource block is will be having 12 resource elements. So here you will be having a total of like 54 cross 12 resource elements. So this is, in this example, I have taken only like one OFDM symbol and like 54 physical resource blocks. So now we are this um, yeah, here you can see that one physical resource block is nothing but one REG, which is having 12 resource elements. So this is a REG bundle. So you can see that REG bundle defined as so this is from the standards. Whatever the REG bundle is defined in the standards, and we are following the same from the standards. So so the combination of six consecutive PRBs, no, yeah, 6 consecutive physical resource elements or 6 consecutive REGs is nothing but one CCE. So this is like CCE 0. This is the first control channel element. And likewise, you will be, as you are having 54 PRBs, you will be having a total of 9 CCE. So it is numbered from CCE 0 to CCE 8. And here you can see that the CCE J consists of the this REG bundle, and these equations. And you can see that function f is a interleaver. So so the thing is, once we are having the closure, now we should know the CCE, or so the CCE indices in which the PDCH is present. So the CCE indices in which the PDCH present is given by the this hash function. So this hash function mostly gives the CCE indices for a particular PDCH candidate. So you can see that there is a variable called MSNCA, which is nothing but the PDCH candidate, particular PDCH candidate. So this is like a non-interleave this CC to REG mapping, where you are having these REGs. All the REGs are like non-interleave, means they are like adjacent to each other. So this is and here the function f of x is a interleaver, and as it is like a non-interleaved process, it's just a function x. So here in the second example, this is a core set. We are having like 2 OFDM symbols and 54 PRBs in the along the frequency domain. See here the CC is whatever the CC to REG mapping is there. It is a time first manner. Means first you can see that 0 1. So 0 is like the first symbol, and the next REG is not in the frequency domain, but it is in the time domain. So 0 1, and the later it is in the 2 3. So you can see this here we perform or say non-interleaved. So interleaved CCE to REG mapping. Here you can see that the CCE 0 consists of the element CCE 0 having these 6 REGs, but these 6 REGs are interleaved. So the interleave where the exact position of these interleaved CCE interleaved REGs are given by the above equation. So this equation is also from the standard, and as an example, this is an example. So where we are using these 2 OFDM symbols and based on all the other let's say variables, this is what this is how the CCE to REG mapping looks like. So here you can see that for like one candidate, so one candidate for aggregation level 4, means for aggregation level of 4, the CCEs occupied are 0 1 2 0 1 2 and 3. For aggregation level equal to 2, the CCEs occupied are 0 1 and 8 9. For aggregation level 1, the CCEs occupied are like 4, like you will be having 4 PDCH candidates, and for aggregation level 1, each like PDCH candidates occupied only one CCE, and first PDCH candidate occupies aggregation level, CCE 0, and the second PDCH candidate occupies aggregation, CCE 4, and the third will occupy like CCE 9 and the other like CCE 13. So now the thing is, we will be looking deep into the CC. So as I said earlier, this CC will be having of like 6 REGs. So in these 6 REGs, actually the DMRs are placed at the first, fourth, and the 8th positions. So now these are the DMRS positions, and we will be extracting these DMRS from the received resource grid. So once we extracted these DMRs, we will be extracting these DMRs from all the REGs. So yeah, we will be extracting these DMRs. So wow, so actually, see, this is the as I said earlier. So this is a typical PDCH, what's a PDCH to DCI like converter. So our blocks will be mostly coming into picture here. Means after the CCE to REG demapping, we will be doing this a correlation between the received and the transmitted DMRS. So how we are generating this transmitted DMRS? As I said earlier, during this connection establishment process, we'll be getting this NID from the base station. So using this NID, we will be generating this transmitted DMRS, and we will be performing a correlation between this received DMRS and the transmitted DMRS. So based upon the correlation, and we will be once we got the correlation, we will comparing this correlation with a threshold. So once if the value is greater than the threshold, then it will go to the RE demapping, and it will do all the other process, so CRC check and everything. If ever it is not greater than the threshold, then it will go for a next change the aggregation level for a given PDCH, and again will do the process. Here you can see that the overhead of every time decoding it until the CRC check has been reduced, as you are doing you are performing everything at the initial stage, like CCA demapping itself. So here, as I said earlier, the maximum number of PDCH, the maximum number of blind decoding. So I think with this achievement, with the limited blind decoding, we can decode the DCI in a limited time interval. So we are actually designed everything individually. Means this DCI to PDCH, whatever the design is there, this has been designed by CIVIT, and we are going, and this whatever the correlation method is there, we have developed the correlation method. And now the thing is, we are working on integrating this design with that actual design, and we are still trying to analyze the effects of this DMRS correlation method. Here are the references, and thank you.
Okay, so thank you, Professor Saif sir and Mr. Venkatesh, so for this wonderful and nice presentation. So the basic concepts of channel estimation and equalization in wireless communications has been discussed in this presentation, and the implementation of these concepts on an FPGA board is also discussed. So signaling and blind decoding of control signal in 5G NR is also discussed in this presentation. So we have one question from Pamila Kumar. Pamila Kumar is asking to Professor Saif, are you planning any contributions to standards? Let us know if you need help to participate in 3GPP or ITU meetings. Professor Saif sir, are you there?
Yes, yeah. Thank you for the very nice question. Actually, so the work with CIVIT is quite an innovative work, but it's actually ongoing right now. So hopefully, once after discussions with the CVIT team, we have some plans of taking it forward. But of course, it has to be along with the CVIT and IIT Delhi together.
Okay, thank you, sir. So with this, we'll wind up this, today's webinar. Great. Thank you, everyone. We appreciate you being here. Thanks again for joining us today, and we will see you the next time. Thank you all.